Hello, everyone, and welcome to Agentic RAG with LangGraph. My name is Derek. I'm with O'Reilly Media, and I'll be helping to facilitate the class today. We'll be kicking things off shortly, but before we dive into the content, I'd like to go over a few quick housekeeping items to help you get the most out of today's session. So first and foremost, at the top right corner of your screen, you'll see a set of widgets. The two we'll be using the most today are the Q&A and attendee chat. You can go ahead and open those up now if you don't already see them open on your screen. Please note that the chat feature should not be used if you're subject to regulated communication restrictions. Also, keep in mind that others in the audience today may include fellow professionals, vendors, or even competitors. We hope you'll take advantage of the interactive tools, but please be cautious about what you choose to share. This course is being recorded, including any participation from attendees. So if you do take part via chat or Q&A, please do not post any personal information like your email address, because that will be included in the recording. You'll receive an email within the next 24 to 48 hours with a link to the session recording so you can review or catch up on anything you might have missed. And finally, at the end of class, you'll see a short course evaluation on your screen. Your feedback is important to us, so if you can take a brief moment to fill out the survey, it's very much appreciated. All right, well, with that, I'd like to turn it over to your instructor for today, Sajal Sharma.
All right, thank you so much, Derek, and welcome everyone. Thank you for joining me for this course on Agentic RAG with LangGraph. So we're excited to go through this with all of you. And even though the course title mentions LangGraph, I want to be upfront about something. The value of this course is not really in learning how to use a specific framework like LangGraph in order to build some agentic RAG pipelines. What I want you to take away is the design principles and thought process behind building flexible, robust, and adaptive workflows for agentic RAG. LangGraph is the tool that we'll be using, but the ideas that you learn here are going to be framework agnostic, and you're free to implement them in the tool of your choice, like LlamaIndex, or even in vanilla Python or some other language if you'd like. And by the end of this course, you'll know how to build RAG pipelines where we use a different sorts of LLMs to adapt the pipeline on the fly. And you will also have internalized how to think about agentic workflows specifically for RAG, meaning that how do we decompose workflows based on different types of search queries that we might encounter in our applications, how to handle failure, or how to design for control, and how to iterate on building these sorts of pipelines. And we'll move between theory and implementation fairly often. And we'll try to ground all the abstract ideas that we see in the slides with the practical walkthroughs of the code in the GitHub repo for this course. All right, so yeah, I mean, before we begin, just want to mention that once we reach the section of the course where I start walking through the code examples for Agentic RAG in LangGraph, I'll go through the GitHub repo and introduce you to the basics, how you can get it running in your own system once we reach that point in the course, right? So before that, let's cover a bit of the concepts that are necessary for us to build this understanding of how to implement all this in code. And before that, let me just introduce myself as well for those of you who have not attended one of my previous courses. I am Sajal. I'm an AI engineer with around 8 years of experience working across machine learning, natural language processing, software engineering, and now generative AI in both product and consulting environments. Right now, I work at Liminal, which is a venture studio based out in Singapore, and I build AI-based products for various ventures here. I also have created the Building AI Agents with LangGraph course for O'Reilly, which you can check out after this course if you haven't already. So this one is an on-demand course. And over the years, I've mentored students at Audacity, University of Melbourne, which is where I graduated from. And I've done a couple of guest lectures at Yale as well on agentic workflows and AI agents. My passion right now is designing composable agentic systems and sharing what I learned along the way on my website, which you can check out here in this link. And I'm reachable on LinkedIn as well as email. So there's a link for these in the slides as well. So feel free to connect with me if you haven't already. And let's take a look at what we're going to cover today. So part one will be a refresher on RAG and LangGraph. And we'll start from the basics. Then we'll build a simple RAG workflow, which will be used as our foundation for the later part. So we will take a very simple use case and add different complexities in the modules 2 and 3 to see how we can build some pretty exciting pipelines. Part two is where we'll explore different agentic patterns that apply to RAG. These are things like query analysis, reflection, and query routing. And we'll build a single agent RAG workflow here with query routing as part of this section. Part three is going to be about combining all the ideas we have learned in part one and two and use them to build full-fledged agentic RAG architectures. And as part of this, we'll look at corrective and adaptive RAG workflows specifically. And we'll build a multi-agent adaptive RAG pipeline here. Okay. So let's get started with part one. And before we get started, let's do a quick poll. So I would just like to know what everyone's experience level with RAG is. I think RAG is a pretty common sort of concept now in AI engineering, but this poll will just help me understand how deep I should go in one of few of these introductory sections. So let's give everyone a few minutes to put in their responses. And after that, we'll move on with a refresher of what RAG is. All right, I think we have enough responses now. So let's see what everyone says. Okay, so yeah, a lot of people who are not familiar with RAG, around 40% of you have never used RAG, but quite a few of you have built some hobby projects and done some pilots at work. And some of you have also built production systems at scale. Not to worry, we'll go through a recap of what RAG is so that you have enough of the foundations to understand the rest of the course. But I would highly urge you guys to, those of you who are not really familiar with RAG, to take another introductory course on RAG on the O'Reilly platform so that you can build up the foundations and address any gaps in your knowledge that you might have. Let's do a quick recap for RAG. So RAG is a technique for enhancing an LLM's output by retrieving relevant context before it generates a response. So since you know that LLMs are trained on static data, they don't automatically know about latest events or your company's private knowledge. And RAG bridges that gap and connects the static models to dynamic real-world information. The retrieval in RAG could be from two places. So it could be from internal sources like your company documents, wikis, databases, perhaps even your personal notes. Or it could be from external sources like public websites, APIs, different sorts of news or RSS feeds, different research papers from something like archive.org, or from real-time data streams. And RAG has two main phases, which are ingestion and inference. In the ingestion phase, we're preparing data for retrieval and indexing it into our database. So this phase is all about preparation to get ready for RAG. And if you're familiar with information retrieval and familiar with how search engines work, it's quite similar. So before you can do searches on your documents, you have to build some sort of index upon which the searches can be performed, like the queries can be processed. So similar to how we have the indexing phase in information retrieval, RAG is, I think, part of the information retrieval domain. So you would have your ingestion step here as well. And as I said, here we're just preparing the data for retrieval later on. And the retrieval can be done by AI agents or some other part of your application. And this ingestion phase starts with loading the documents into our index. And the documents in their raw form can be plain text, PDF, HTML, Markdown, or even images if you're dealing with the multimodal RAG. We're not going to be covering multimodal RAG here, but the concepts are quite similar in how they can be applied. Another way to handle non-text elements like images or tables, I mean, you can either generate some sort of embedding representations of the images directly, or what you can also do is something called serialization, which means that you can convert them into a textual representation so that they can be processed. So one of the things I like doing in certain projects at work is if you have an image and your image has, let's say, one of the use cases that I encountered was that we had to do some sort of RAG search on PDF files, which talked about company portfolios or perhaps their organization structures, like how many people they have, where they're located, and also those sorts of things. And a lot of times what happens is that that information is not really in clean text in the PDFs as well. It's usually in something like a super complicated chart, right? Like there could be like this hierarchy chart that, okay, this is the CEO, and like there is this like vice president under here, there's like the CTO. So this is how the information was represented. So one thing I like doing is serialization, which is that we want to turn this information into text. And the easiest way you can do this is you can pass that image into some sort of an LLM. I find that the Gemini models work quite well for this, and ask them to just create a clean textual representation of whatever is in the image. So what you'll get is like some sort of paragraph about what the, for this example, what the company's organization hierarchy is. And then whenever you want to, search about who's the boss of, let's say, this person, this text should have enough information to be retrieved later on, right? So serialization helps us do this. It helps us convert images or super complicated structures not inherently suitable for search into something that can be suitable for this. All right, so this is about serialization. But this is an optional step. I mean, it depends on your use case if you would need to serialize or not. What's not optional usually is chunking, which means that here we break down documents into manageable pieces. And usually a manageable piece can be anything around like 1,000 or 2,000 tokens. Or you can also chunk documents into some predefined structure. And this helps keep the retrieval precise and relevant. So even though we have LLMs that have 1 million token or 2 million token context windows these days, chunking can still help the LLMs, at least in terms of retrieval augmented generation, by making sure only the relevant information is passed on to the LLM. And whatever we're passing on to the LLM, it doesn't contain noise. It doesn't contain, if let's say we have 1,000-page PDF and all of 1,000 pages still fit into the context window, not all of the 1,000 pages would be relevant based on whatever task is being done by that process at that time, right? So chunking can help keep things manageable and relevant for the generation step later on. Okay, and once we have the chunks prepared, we can generate embeddings for each chunk so that we can do similarity searches. So embeddings are high-dimensional vectors of numbers, and they give a sort of common representation for each text based on the embedding model that we have used, so that we can do some sort of semantic search on those vectors. So when a query comes in during the retrieval augmented generation process, we want to find similar documents. Embeddings allow us to use things like calculating the cosine similarity, for example, to get a sense of how relevant each ingested chunk is to a given incoming query. All right, and then once the embeddings have been generated, we store these embeddings and persist them in something called a vector database. And vector databases, you might have heard of different examples of these, like Pinecone, VB8, ChromaDB, etc. And vector databases are databases which are optimized for performing vector search. They offer different kinds of advanced indexing mechanisms to be able to do fast similarity search on millions or billions of documents. All right. And this is what the pipeline looks like in its like simplest form. It's a simplified diagram. Many times you'll have much more complicated things going on here, but you can think of these as your raw documents. And once your raw documents go through this optional serialization step, you chunk them, you generate the embeddings of those chunks, and then you ingest or index them into your vector DB so that it's ready for querying. All right. And once the data is ingested, we move to inference, and this is where user queries start coming in. So the key steps here in this phase are, first we have query processing and enhancement, and this involves understanding the intent of a query, extracting any metadata filters, maybe expand or break down the query if needed, or generate hypothetical documents for this query, which is an advanced technique. So we won't cover it here. But these are all things that are useful in sort of improving the accuracy of your search. Once your query has been processed and enhanced if needed, we can do an initial retrieval, which includes finding the top K candidate chunks from our database using vector or hybrid search. And sometimes we also re-rank those results to improve the quality of the set of documents that we have retrieved. And finally, we feed the retrieved context into the LLM to generate a response that's grounded in the data that we have just pulled in, right? And it's simply the simplest form of non-agentic RAG pipeline looks like this, where you have a query, you do some retrieval from your vector DB, you get relevant documents, then you feed those relevant documents along with your query to a generation step, which calls an LLM, and then you get a response. It might be the result, or it can be some augmented response that is generated by the LLM that you have passed all this context to. And as I mentioned, RAG still continues to be relevant. Perhaps the ways RAG is done is changing, and the ideas around, do you still need vector databases? Maybe things like Cloud Code can just perform RAG on file systems. All of these can change, or there might be new ways of doing RAG, but the concept of RAG is still relevant. And the reason for this is that while the models are getting larger and larger and context windows are expanding, these models still have some sort of knowledge cutoff, and these are old ones. The newer models like GPT 5.1 or Claude 4.6, those might have more latest cutoff dates, but they'll still be older, and that's because it takes weeks or months to train a foundational model. So how training is done right now, due to the whole process of how that happens, we can't really expect the models to know anything after that happens, after those dates, right? And even if the models have some way of knowing, right, they still won't have access to your private information that they have never been trained on, right? And even though we have huge context windows, as I mentioned, the LLM still have some sort of lost in the middle problem. And this really happens because of how the transformer architecture is laid out. And again, this is not something we will go into detail, but what happens is that when doing generation, when your LLM is performing inference, when it's generating some sort of response, given some input, the transformer architecture, it pays attention to each and every token in your input. So if you have a 2 million token input, then the model will still try to pay attention to each and every token in there, right? And that, as I mentioned, may not be relevant for the purposes of the task that is being performed. So it's always helpful to make sure that only the most relevant data is being passed to an LLM and not everything under the sun. Like we don't have to cover the context window limit. It's like the maximum. It's not that the input should be of this size always, right? And even let's say if it was possible to do really well on accuracy when using these large context windows, you'll still have high costs associated with it. So because how these foundational model providers right now, they charge us by the token. So you want to make sure that you are being efficient in how many tokens are used in your application, right? If you're not, then you run into the problem of very high costs of just keeping your system operational, which may or may not make business sense to you. There are still hallucination risks with models, and without the right context available to these LLMs, they are prone to making things up, which is especially risky in regulated industries. No, I don't hear a lot of people talking about hallucination these days, especially on LinkedIn. Maybe it's a like a old problem, and people think that it has been completely solved. But in the types of applications that I've built, like both for work and for just like playing around, I still see hallucination crop up a lot. When like one of the funny things is that when an LLM is desperate, it sort of tries to produce tokens that sound like facts, that might be rooted in real data, but more often than not, it will be not. Right, so you still want to use something like RAG to make sure that the LLM is producing factual or like factual sounding statements based on data that is really grounded. And there's also the issue of knowledge needs being very dynamic. As I mentioned that you have data that changes quite frequently, like financial markets, news, academic research, coding documentation as well, even like software engineering tools like Codebase, right? So these are things that you can't really just embed into a model just by training, right? So you still want to use some sort of way to augment the LLM's knowledge. And internal documentation, policies about your company, proprietary information, all of those the LLM will not be aware of at all. So RAG is again the way to keep your AI answers up to date. So you should think about RAG as a way of like making sure that your LLM has the knowledge it needs to perform a task correctly. And it'll still continue to be relevant as long as we have we have the need to pass the LLM some latest data or some really contextual data based on the task that it's doing. Even things like OpenClaw or these other sort of new agents that are coming out, like OpenClaw is sort of like a personal assistant, and people are using it to do things like manage their calendars and other sorts of things. It still uses retrieval from some sort of APIs and command line tools to get information out of your calendar and do some things with it, right? So that's still some sort of retrieval, and it's still being augmented with that information to perform tasks. So RAG, I think, is an evergreen concept. I don't think it'll disappear. It is a necessary part of how AI applications are built right now, and it will continue to be for the foreseeable future. All right, and the other question that comes up is, why not use fine-tuning instead of RAG? And compared to fine-tuning, RAG is more cost-effective since no retraining is needed, and you don't need a very complex infrastructure, and there's a lower maintenance cost involved with not having to fine-tune or train any sort of models at all. It's quite flexible since the access to its knowledge is sort of decoupled from the training weights. So you can update your vector DB independently of how the rest of the application is laid out or how the rest of the system is laid out. And your model will have the access to the latest information just by updating the vector DB, right? You can have some sort of granular control and version management in your documents that are ingested as well. And by granular control, I mean some sort of access control where, let's say if you're building like a very simple use case, but let's say if you're building a chatbot or support help desk for some sort of enterprise, and you don't want HR documents, internal HR documents, to be available for anyone outside the HR department. So RAG can help you do that. But let's say if you were to fine tune a model and embed the knowledge in your model's weight, it gets quite hard to control the model in like not divulging that information for non-relevant use cases. And you can also trace the different sources. You can trace the outputs. You can audit them. You can figure out where exactly which documents information came from, because it's quite easy to visualize that, to log that information in your information retrieval pipeline. All right, so this was all a recap on RAG. Now, I know that there's like a lot more that can be covered in a course just about RAG, but this is not just a course about just RAG, right? Like, it's a course about agentic RAG. So we're going to focus here more on how we can take concepts from how we build AI agents or how we build agentic workflows and apply them to the problem of retrieval-augmented generation. So as I mentioned before, if you are completely unaware of the basics of RAG, I highly encourage you to take one of the many courses available on the O'Reilly platform for that. And here we're going to focus on the agentic mechanisms that we can apply on RAG and how we can do it using LangGraph. So before we jump into agentic RAG in particular, let's get a sense of how many of you have used LangGraph or any other sort of LLM orchestration framework before. So I'll, again, give everyone a few minutes to put in their responses. And once we have enough responses, we'll move on. And also keep your questions coming in. Whenever we take breaks upon every hour, I'll go through all the questions that have come in up until that point in time before we move on to the next segment. Okay, I think we have enough responses now, so let's see what everyone says. Okay, so about like 3/4 of you are aware of what LangGraph is or have used other sorts of LLM orchestration framework. And a lot of you haven't. About 1/4 of you have never heard of LangGraph or used it. So for those of you who are familiar with LangGraph, I think the stuff that's coming on now will be something that you're just recapping. But I think it's useful to just go over the basics of LangGraph once before moving on, so that everyone knows how these agentic RAG workflows have been structured by us, right? So let's do a quick recap. So LangGraph is a framework for building agentic workflows with LLMs. And it's a graph-based framework, which means that you can design your workflow as a directed graph using nodes and edges. And you can also include cycles for iterative processing in your workflow. So this is a cyclic directed graph. It's stateful. The state of a graph, meaning a snapshot of what data is represented in some stage in the graph, is persisted, and it is carried through the execution steps. That means each step can remember what's happened so far and adapt accordingly. It also has built-in capabilities for persistence, streaming results, bringing humans in the loop when needed, and a lot of LLM orchestration frameworks will, I think, provide similar capabilities to this, but they might use like different teams for different techniques. And I think using a framework can be good if you don't want to care about building the scaffolding that's required to build LLM applications yourself. There's, again, a trade-off in whether you want to use a framework or you don't want to use a framework and write pure Python for it. I think using frameworks, if it's aligned with the sort of architecture of your system and what you're building, makes sense. If there's a framework of your choice available that suits your design, it can help you go faster, and it sort of like also I think helps manage the. I like to think of it as the knowledge of how things are represented. So if let's say like a simple example, I find it way easier to just like like build workflows like this. Um, and this is basically what LangGraph is, right? It's a graph of nodes and edges. So I find it easier to visualize the sort of life cycle of an agentic workflow instead of like having to read 3 different files of code and try to make sense of which function is called when, and try to build the data passing between each of these myself, and like build all the things that frameworks provide you baked in, right? Like persistence and streaming. So depending on what you're trying to build, a framework may or may not be suitable for you. But I think it's always a helpful way to just get started with building. Of course, there's some sort of learning curve there, and the learning curve is different for each framework. But I think, especially for LangGraph, I think just by thinking about it in terms of, okay, it's like a graph-based execution workflow, makes it easier to digest. And LangGraph actually gives you a lot of control on building the kind of things that you want, right? So even though LangGraph is actually marketed as a framework for building AI agents specifically, it's actually a quite useful framework for building agentic RAG workflows as well, as we'll continue to see. All right, so let's discuss some of the building blocks of a LangGraph workflow. And the basic building block in LangGraph is a node. Each node is essentially just a Python function that processes the state and transforms it and creates some sort of output. It takes the current state as the input, performs some logic, and then returns the updates to the states. And these state updates can be partial or complete, which means that it might choose to update just like attributes in the state, or it might choose to update the state completely. And I keep saying state, and maybe I have not introduced it. We'll see what state means in a second. But what you guys can think about being a state is just being like some sort of Python dictionary or hash map where you have key value pairs. And your nodes will choose to, let's say, node A might choose to only update this key value pair and nothing else. Node B might choose to update everything. And this depends on what sort of processing a node is doing based on your state, all right? So that's what I mean by partial or complete state updates. All right, and again, like since we're using, since a node is essentially a Python function, or if you're using some other LangGraph in some other language, it's just like a function in that language. And it can contain any logic. It can contain LLM calls, tools, any other sort of Python processing, whatever you want, right? And here you can see an example of a node where we retrieve some documents from a vector database and update the state with the retrieved documents. Okay, so in this node, we can see that we take the query from the state. And again, since I mentioned that, like, the state is like a hash map. So we get the question attribute and, assign it to our query variable. And then we do a similarity search on our vector store based on that query. We get some documents back, and then we assign it back to this context key in the state. The second building block of LangGraph are edges, and edges define how workflows move from one node to another. We have different kinds of edges. There are normal directed edges that always go from one specific node to the next one. And then there are conditional edges where the path depends on the state. You also have entry and exit points to mark where the workflow starts and ends. And in this code block, you can see 2 examples, one for a normal edge, which connects a retrieve node to a generate node, and one for a conditional edge, where we use a routing function to decide the next node to execute. So if it's a simple query, we can execute the direct response node using an LLM. retrieve the docs for a complex query, or ask for clarifications as needed. All right. And we'll cover some of these in our coding examples as well. So don't worry if it doesn't completely resonate as of now. The last core block of LangGraph is the graph state. So LangGraph uses a shared state object that all nodes have access to. And this state is persistent, which means that it's maintained across execution steps. It's usually strongly typed with something like a type-dict class or a pedantic model. So you know exactly what data is available and in what format. And you can control how updates are applied to the state using something known as reducers. So reducers are also functions that update your state. So for example, whether new data from the result of the processing in a node, whether the new data should overwrite the old data, or should it be appended, or it should be merged. So you can use different types of reducers for different sorts of these actions. And we have another code example here where you can see a basic state for a RAG workflow, where we keep track of the user query and retrieve a list of documents, the generated answer, any other sort of metadata, etc. Right? And earlier you saw that simple workflow that we have for RAG, where, let's see. So if I could just bring your attention back to this slide where we had this simple workflow. We have the user query. We have some sort of retrieval happening. We have some relevant documents that are the result of this retrieval step. We have the generation step after that, and then we create a response. By the way, you can see that this is a graph, right? And that's why I like LangGraph so much, because it's quite easy to sort of visualize and then build these sorts of workflows using LangGraph. So you can see how we're keeping track of these things, right? Like we're keeping track of input, the relevant documents, response, and there might be like some other intermediate steps that happen here in an Agentic RAG workflow. So similar to what you see here in the slide about the state, you can see that, again, we're keeping track of, the three sorts of types of data that are relevant to making sure that the workflow is doing the things that we want to, right? And we'll continue to see this pattern where, when we're just designing the workflow, that there are like these 3 steps. It needs to keep track of 5 data points. Okay, a state is just, a Python dictionary or a hash map. Just like designing, even before you start writing code, becomes very easy to do. And honestly, I think in the age of all these coding agents, I'm not writing any code by myself these days. Of course, I use Claude Code or Cursor and whatnot. I think just the act of designing your sort of functionality, designing your agentic workflow before even representing that in just pure code becomes even more important. So this is one of the things that you have to do in LangGraph, as we'll see. You have to like design what you want to do first, and just the code is just like a compiled version of like the graph that you can visualize. All right, so now that we have covered state, let's just take a look at how the whole process works of defining a simple graph in LangGraph. So you start by importing the required classes from whatever module that you needed. We won't go into super detail about that. But what I want you guys to focus on is the different steps. So step 1, again, you're designing, right? So you just think about what sort of data the workflow needs to track, what different changes will happen in the state. So for a simple RAG pipeline, we just need to track the question, context. Again, this can be a list of documents. The question can be a string, and then the final answer that is generated, which can, again, be a string. By the end of this course, you'll see us building a very complicated agentic RAG pipeline, which will have, again, a very, very, very complex state. So stay tuned for that. But again, let's start simple. So once you have defined the state, and we are defining it using a type dictionary class, you create something called a builder object. And this is just an instance of the state graph class. And we pass in the state class that we have defined above. And This object basically keeps track of what nodes and edges are there in your workflow and how they are connected to each other. So once you have created this builder object, you can start adding nodes. And you add a node by using the .add node method. And it takes 2 arguments. It takes a function, which is the Python function. And you must have defined this before this step. And it takes like some sort of string representation, string ID of what the node is meant to be. All right, so it takes 2 arguments, the name of the node, or you can call it, and the actual Python function that represents the node. So we add 2 nodes for retrieve and generate. Then we define the edges between the nodes. So since we have imported the start and end nodes here, you can think of these as the start and end points. There are different ways to do this in LangGraph. I find having the start and end node explicitly defined much easier. So you start by adding the edges between the nodes. So we add 1 edge between start and retrieve, then 1 between retrieve and generate, and then finally from generate to end. And then once all the nodes and edges have been added to this builder object, we compile the builder object and it gives us a graph. And then we can use the graph by passing it some sort of query, and then that query will sort of go through all these steps and generate like some final output at the end. And we'll see an example of that as well. So we have covered how a basic graph can be built in LangGraph, and this is actually a retrieval-augmented generation graph. So now that we know what we're going to build, let's go over to a Jupyter notebook to see how we can create a very simple RAG workflow using LangGraph. All right, so we'll have time for questions after this. So let me just share my screen. Okay, so this is the GitHub repository for this course, and you should see the link in your course resources. But if you don't, I'm sending it again in the attendees chat as well. But feel free to don't worry about following what I'm doing right now. I think you can use your favorite coding agent like Claude Code or whatever to go over the repo and try to understand or fill in any gaps that you might have in knowledge. But for the duration of the course, what I would like you to do is just to follow along in the explanations that I have for the different sort of use cases or agentic RAG pipelines that we are building, and just focus on the design of things, not really about how the code is written and how the code is executed. I think that all is a secondary. Design is more important, at least for these sort of things. So when you go to this link, you'll see the GitHub repo. There are some prerequisites for actually using it. You need an OpenAI API key, because that's an LLM that we're using for the course. Your API key, and we use Tavily for web search. So this is one of the AI native web search services. There are others out there, but Tavily is the one we're using. You can get a free API key if you go to tavily.com with like 1,000 requests or something, which is more than enough for this course and any sort of experimentation that you might want to do afterwards. And once you in the repo, you'll need to make sure that you have UB installed, which is the Python package manager that we use. All the dependencies for this repo are also installed. Then you can just configure your environment variables like this. And there's a .env example file that you can use to update your environment variables. And then once you have done all this, this is the most important step for running this repo, which is setting up the vector databases. So this course, Agentic RAG, is mostly what happens after we have ingested our data. And we're, of course, going to be focusing on the inference, the search step here, right? We're not going to be focused on indexing. So what I have done is I built 2 scripts here to ingest the data for this course for you. So in the course, we have some raw data that I have sort of asked different LLMs to curate. So we have data for TechMart, which is a fake company I made up. It's an e-commerce company that sells electronics. And we have three sorts of CSV files here. We have a catalog for TechMart, which is basically the products, SKUs that they have, like different like pricing, descriptions of the products, etc. FAQ pairs, which is basically question and answers for different sort of products. And then we have a troubleshooting file as well, which contains like different information about different issues people might face when you send like some troubleshooting instructions as well for that. So we have like three sorts of data files. Use case that we're trying to solve is a customer support chatbot. So for TechMart, they have a AI assistant, their website, and people can ask questions about either the products that they have or ask some like questions about shipping or return policies, or they can ask questions about, oh, I'm facing problems with my Ultrabook Pro about the battery or like the etc. So these are like the three use cases that the customer support chatbot is supposed to solve, right? And based on these three data files, which is in the data folder, you can check it out. If you just follow these steps listed here, install the dependencies, etc. And what this will do is it will go through the RAG ingestion pipeline automatically, and it will index the documents into a vector DB. So we're using Chroma DB as our vector database here. Again, it doesn't matter which vector DB you're using. You can really very simply adapt all of this code here to like Pinecone or VB8 or Quadrant, whatever vector database you use. We're using Chroma because it's the easiest to teach with. It's the most portable. And once you run the script, it will ingest it into a locally running Chroma database. And then we're creating two sorts of collections. So collection basically means like a table inside the database, right? So this script, it will insert all the documents into a single, you can think of a table. And this one will create three different tables for the three different types of documents that we have, right? So we'll have like product catalog, FAQs, and troubleshooting, all of these in separate tables. And once you have ran these two scripts, again, we're doing this, by the way, just for like teaching and making sure that you all can understand like different sorts of problems that can happen based on how we have ingested and like structured our data and how Agentic RAG can solve those problems, right? So this mostly like setup. Don't think of it as, please don't use this code to ingest your actual production pipelines, right? So once you have ingested everything by running these scripts, you'll see that the ingested embeddings and documents, these are located in this vector store directory under the ChromaDB single folder and ChromaDB separate folder. And Chroma uses SQLite, at least locally, in the backend. And if you actually go above, and there should be you can't see any vector DB folder here, but you'll see in the Jupyter notebook instance that I'm running, there should be a vector store folder, right? Because that's where I have ingested. I haven't pushed the ingested files here because, again, this is something that you have to create on your own. And that's it. Feel free to just like ask more questions about how this repo is structured, what sort of data is there using the coding agent of your choice. And assuming that once everything has been set up, that's when you can start going through these three notebooks that we have, right? And we basically have, like how the course is structured is that we have three modules, as I mentioned, and there's one notebook for each sort of module to build the things that we talk about in the slides, right? So you'll have one for basic RAG, you'll have one for agentic router RAG, and then you'll have a third one for agentic adaptive RAG, which is the most complex agentic RAG workflow that we built. So with all that being said, let's check out the first notebook, which is just building basic RAG pipeline with LangGraph. All right, so in this notebook, I hope that this is zoomed in enough for everyone. Okay. Okay, so once you load up this notebook, you can start running the cells. I have pre-ran this earlier today. I won't run it again. Some of these cells can take a long time to execute and will just be wasting time. But if you set up everything according to the README correctly, then it should all run for you. So once you have set up everything, once you start running the cells, you'll see that, okay, the environment variables have been loaded. All the imports have been loaded successfully. The environment variables have been set up, including the OpenAI API key. So we use the OpenAI API key for two things. We use two models, one for the embedding model that we use, and here we have chosen to use text embedding small, which is enough for this toy example that we have for learning. In production, you might choose to use text embedding large, perhaps, but for this, small is enough. Then if you have like images or something, you might use a multi-modal embedding model, but again, the actual pipeline would be the same. So we initialize the embeddings model first, and we need the embeddings model both in the ingestion phase as well as the inference, the query phase, because when a query comes in RAG, you need to create the embedding of the query, because you will do the similarity search using the embedding of the query, right? You want to look for embeddings that are similar in documents that you have ingested, similar to the embedding of the query. Okay, so that's why we initialize the embedding model. We connect to the ChromaDB instance, and we just pass the path where our ChromaDB is located, and you just see it being loaded correctly as well. And we have like a number of documents that are in our collection. And then you can just simply do a test run in your vector store to make sure that at least the similarity search part is working. So we haven't built anything using LangGraph yet. We're just checking if our vector DB works correctly. So for this query, when will my order be delivered? We run the similarity search method on our vector store on the query, and then we get our results back. Now, this vector store object actually comes from a class of ChromaDB, and we simply pass in, we're using the Python SDK for Chroma. We're actually using the LangChain wrapper library on top of it for Chroma. But again, this is not necessary. This is one of the simplest ways to do this. But Chroma has a Python SDK as well. If you don't want to use LangChain, you can just use that, but the steps will be similar. So we create an object of the vector store. We pass in the collection name we want to use. We pass in the embedding function, and then we pass in the directory where this vector store is located in, and you can see that it's loaded correctly, right? And then when we run the similarity search, K represents the number of results or documents we want to retrieve, and this will return the top K, the top 3 documents, as we see here. So for the query, when will my order be delivered, you can see that the 3 relevant documents are actually, they sort of look okay. The first one is, how long does shipping take? Okay, yeah, looks relevant. Can I track my package after it ships? Yeah, also relevant. Do you offer next day delivery? I think also relevant, right? Like if someone is asking about a specific form of delivery for laptops. So you can see that our vector search is working quite well, right? It's retrieving relevant documents. And now all we need to do is to build some sort of a generation on top of this retrievals. So we'll continue doing that, right? So in order to do that, we initialize an object of our LLM that we want to use. So we're building an object of the chat OpenAI class. And again, chat OpenAI is a wrapper on top of the OpenAI library that works quite well with LangChain. This comes from LangChain. You don't need to use LangChain again for this. I'm using this because it's one of the simplest ways to get started with. You're quite free to use the OpenAI SDK, Python client SDK directly if you choose to do so, right? But we're using chat OpenAI here, which is the LangChain wrapper. And we simply pass in the model, the API key, and like the temperature that we want to use. And if you're aware, a lower temperature usually means that we see more consistent and like less sort of randomized responses. And we're using the GPT 5.1 model here. You're free to use the latest 5.3 or 5.4, I think now, models that you want. But I'm choosing to use 5.1 because I want to do this using a cheaper model. So once you have defined this object of your LLM class, then what you want to do is to build some sort of prompt that you would send to the LLM, right? And here we define the prompt template. So prompt templates are basically format strings in the world of LLM applications and like AI engineering. These are sort of strings which have placeholders for different things that you can inject or hydrate your format string with. So for this prompt that you are a helpful assistant for TechMart, blah, 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 we're passing in two sorts of inputs from our side in code, which is the context. And this is like the documents that we would have retrieved in the retrieval step. And then we're also passing in the question, which is like, what is the actual user query? So this prompt template is the prompt template for the generation step, right? And once we have described and built a prompt template, we can use it to pass in our inputs, and then we can pass this to our LLM, and it should be able to use this resolved or hydrated filled in block of text to do some sort of inference. Right? So once the prompt template is created, we define the state for our LangGraph workflow. And again, like you must have seen this twice already. We have the question that we're keeping track in the state. We're keeping track of the context. So this context we can see is of the type of list of documents. And this document type actually comes from LangChain as well. But like this could also have been a string if you were passing in a list of strings, but we would need to do some extra processing there. But it's not necessary because if we pass in the document this way, since we're using LangChain, it knows enough to resolve that to a string when it's passing it to an LLM. Right? So once our state is defined, we start creating the nodes. So we create the retrieve node first. And this retrieve node, what it will do, it will take the question from the state. It will run the vector search, the similarity search on the question. And here we're choosing to retrieve the top 5 relevant documents. This case will again depend on your use case, the different trade-offs you can have in your K. Having a larger K increases cost and increases latency, but it might give more spread for your LLM to find the knowledge it wants. But I think 5 is an okay number to start with. And what we also do in this node, just for debugging, is to print the first 100 characters of each retrieved document. This is not necessary. This is just something that we have for logging here so that we can see what's going on under the hood when we run this workflow. So once our retrieve node is created, we create the generate node as well. And what you would see is that for like both these retrieve and generate nodes, these are just like Python functions, right? And these are just taking the state as the input. And like we have, actually like defined what the type of the state object is. It's like RAG state. And, we define RAG state here. Fine. And we can also define like what it returns, which is, the updated state. But that's all it is. It's just a Python function. In the generate step, what we basically do is we get the context, we get the question, we get the context documents, both from the state, and assuming that this generation step will happen after the retrieval step, this will already be filled in. This is some simple string formatting code to make sure that we're combining all the documents and just like creating a single string format, as you can see here. And then we're just like making sure that the documents are separated by new line characters. We clearly know what the source of the document is, what the context of the content of the document is, so the LLM has enough information to use that appropriately. Like some simple form of context engineering here. And then you just, create the prompt with the context and this RAG prompt is the prompt that we had defined earlier. And once we run .invoke on the prompt, it will simply create this final string, which will have, like the actual list of docs and like the actual question here, right? So that's what happens after running .invoke on this prompt template. And we're just passing in the inputs for the format variables. And then once we have this, we can just run .invoke on the LLM object. And invoke is basically like execute, right? Okay, just like run this prompt template, run this LLM object using some sort of input. And this will give us the response back from the LLM. And we'll see like what happens in all these steps soon. And then we build our graph. This is exactly the same that we had in our slides. And there's no changes here, right? We add the nodes, we add the edge from retrieve to generate. And this is an alternative way of adding the entry and finish points. So instead of importing the start node and the end node, you can simply set entry point and the name of the node that should be the start node connected to the start node essentially. And then you can do something similar to the last node in your workflow. And then you compile your graph. And one of the good things about LangGraph is that you can visualize what your graph looks like. And you can see here that, okay, this is right out of our slides. You have the start node, you have the retrieve node, the generate node, and we end here, all right? And then once all this is compiled, all this is defined, we define a simple helper function to run our workflow. And then we can simply run execute that graph that we have compiled using .invoke again, right? So in LangChain terminology, .invoke is what you use to execute your prompt template or your LLM or your graph workflow, all right? So we pass in the initial question, and that's we print out the result in this function, helper function. So if we run it with the query, how long does it take to ship to the US? You can see that this query retrieves all these documents. How long does standard shipping take within US? Which countries do we ship to? I think these are like more or less relevant. And then it generates this final answer that within continental US, TechMart's standard shipping typically takes 3 to 5 business days. All right, I think it works well for this question. So good enough for now. Let's ask it a different sort of question. So as I mentioned in the start, how this problem statement is set up is that we have a customer support chatbot, and it should be able to answer questions about 3 things. About, like, of course, the frequently asked questions about shipping, which is the first example, and like return policies and what. But also answer questions about the product catalog. And this is what this example is. That what are the specs of the Ultrabook Pro 14? So we can see here that okay, good. It is actually retrieving data from this TechMart catalog.csv. This is the original source of the information. And we can see that, okay, it was able to find the exact laptop that we wanted to see. And then in the answer, you can see that it's printing out the specs of the Ultrabook Pro laptop, and it works quite well. And this question also works quite well. Like my mouse is not working and it's a technical support question, which is the third use case type. So all good up until now. And then when you're running this notebook, you can try asking your own questions here and see what the results are. But let's see like a couple of examples of where we can start running into problems with this very simplistic setup. So all of our documents right now are ingested into a single vector DB index. And this is the idea of the single table, single collection within the vector DB that I just mentioned, right? So the product catalog, the FAQ, and troubleshooting, all of these live in a single vector DB index. And there can be certain problems that happen in that sort of setup. So, yes?
A lot of people are noticing some video lag and also some choppiness. Can you reconnect and then maybe just keep your camera off when you're doing the screen share and see if that helps?
Okay, let me turn the video off. All right, so can you hear me right now, Derek?
Yes, I can hear you.
Okay, and is the video okay or still choppy?
It's hard for me to tell. Maybe you could try typing something.
Okay. Okay.
I think it's better. I'm seeing some comments of
Yeah,
people saying that it seems
people
better.
are saying that it's better now. Okay, I think it's a problem with both the video and the screen share being on at the same time. Perhaps the bandwidth is not able to handle it for some reason. Okay. All right. Thanks, guys. Sorry about that. If you also don't mind me asking, what was the point at when the sync and choppiness issues started happening, so that I know where to resume from? Were all of you able to see the visualization of the graph that we built? Okay, I will assume that means yes. So we'll carry on from the point where we built our RAG system using LangGraph, the basic RAG system, and when we started testing some queries with it. Okay, awesome. Cell 10, right? Awesome. So yeah, so this cell basically builds a helper function where we can ask the question from our RAG workflow and just print out the results for that, print out the final answer. Okay. The first question that we asked was one that could be answered from the FAQ documents that we have. And this question is basically, how long does it take to ship to the US? And for this query, you can see that we retrieve 5 documents here. And most of these look quite relevant. How long does shipping take within continental US, etc. And you can see that the final answer is also correct. Right? That the TechMart standard shipping typically takes 3 to 5 business days after your order has left the warehouse. All right, all good here. We can also ask a question for a different type of data in our index. So here we are asking the question about, we're supposed to answer a question from the catalog we have. So we ask the question that what are the specs of the Ultra 14? And just give me a second. Derek, do you want to mute your microphone?
What was that?
Do you want to mute your microphone?
Oh, apologies.
Yeah, no worries. Thank you. All right. So yeah, the second example was that, okay, we ask a question from the catalog, right? And we can see that this also works quite well, that we want to know the specs of this laptop. We can see the most relevant document being retrieved actually in the topmost spot. And then the answer being generated also being quite correct, right? That it takes the exact specs of the laptop and we can see the results. Okay. And this will also work well. Like there's a question about the troubleshooting data, and it'll also work quite well. So no need to cover this. But what's more interesting is the sort of questions that we will see don't work quite well. Like what sort of limitations we hit when we have a basic RAG pipeline. Okay. And if you just scroll down, like instead of talking about all this, let's just see some examples. So in this query, we ask, do you have Bluetooth headphones and how fast they can be shipped within the US? So like, there are like 2 questions in this one question, right? The right way to handle this would be to break this question down into 2 questions and then sort of try to retrieve the documents individually. But of course, we have not built all of that up until now. And what we can see happens here is that we try to retrieve documents for both, for in a single RAG pipeline, in a single search essentially. And even though we see the result here that, okay, we were specifically asking that how fast can headphones be shipped within the US, we can see it's actually returning the topmost document that has information about the delivery or shipping for laptops. So this is incorrect. We would want to know if we have shipping information specifically for Bluetooth headphones, right? And in the answer that is generated, you can see that, okay, it says that we do carry Bluetooth headphones and we can ship laptops within next day delivery. This is not really relevant to what the user asked, but again, like, the LLM doesn't have the knowledge that it can use to answer the question. And it says that the context doesn't have the exact shipping speeds, right? So you can see that that's one limitation we hit here. This is not really useful. Another sort of question is that when the lines are a bit blurry about what sort of question is being asked by a user. All right, so here we ask that, okay, Ultrabook Pro charging ports. Now, this is a very vague question. The user might be asking about what charging ports that the Ultrabook has, right? And it's a very relevant question. If it charges via USB-C or via something else, via USB 3.0, whatever, you could have different charging speeds. You can have like 2 charging ports or a single charging port, etc. So it is a relevant question. But it can also be a question about, hey, the charging ports on Ultrabook Pro are not working, right? So it's inherently a very vague question. And you can see that it's retrieving documents from the troubleshooting type. And you can see that all these documents are of the troubleshooting type. And it's actually also not able to find any troubleshooting information about the Ultrabook Pro. So it just, gives a completely irrelevant answer. And perhaps what would have helped is that, okay, if a user asks a vague question about the specifications of a laptop, we can make an assumption that, okay, they're perhaps asking about the product information. They're not looking for help at this stage, right? But like a simple RAG pipeline, of course, is not able to inherently answer that. It's not able to like adapt to the different types of question which might be asked, even though, we have like different types of data in our DB, right? Let's just cover one more. So in this question, that what's your return policy for monitors? You can see here we have like a different sort of problem. So for this query, we see that the first document is about the return window for monitors, and return window for like everything, mostly, like not specifically for monitors. But we have a lot of documents that are also retrieved that are about like product, different types of monitors, different like items from our product catalog, right? And like some data about receiving a damaged product, etc. So there's like some amount of noise here, and this sort of noise can also be detrimental to the LLM. Like if we know that we have retrieved documents that are not really relevant, it doesn't make sense to pass all those documents to the generation step, right? So that's like a few of the problems that we can encounter. And like we have like one more example here. So if we ask a question about what's the battery life between these 2 different laptops, like can we compare that? You will see that in the retrieved documents, we are not retrieving Ultrabook Pro at all. Like all of our results are from Zenith Book. And then you'll see that, the model is not in catalog, or like I don't have information from it, which if you look into the data is actually incorrect. We actually do have specs for this. And if we were able to find this document correctly in a RAG pipeline, then we would have answered this question correctly, right? So this is a problem within the pipeline that we have built. It's like too simplistic or not really tuned enough to be able to answer these sort of questions. So the final point is that, yes, we can build very simple RAG pipelines, but there can be like different sort of problems that can happen due to different sorts of reasons. And what we'll build in the next few modules is try to solve those problems by adding different types of nodes or different sorts of components to our RAG workflow. All right. So this is the problem that we'll be solving in the next few modules. So it's been I think little more than an hour in the class. Let's take a 5-minute break. And when I come back, I'll answer a few questions that I see on the Q&A channel. And then we'll move on to module 2, where we add some agentic capabilities to our RAG pipeline and solve some of these problems that we have started facing in our simple pipeline. All right. So let me just start a 5-minute timer. Okay, all right. See you all in 5 minutes. Take a water or a tea break, and we'll be right back. All right, we're done with our 5-minute break. So let's go over some of the questions now. So let's answer this one first. Okay, so which LLMs can be considered for image embeddings? OpenAI Clip. So yeah, like different models are used for like different sorts of representations, essentially. And I think the best models that can do these sorts of multimodal embeddings keep changing quite frequently. OpenAI's Clip is one example, but it's also quite old, I think. So what I implore you to check out is just announced yesterday, the Gemini 2 multimodal embedding model. So that model aims to sort of create embeddings of text, images, audio, etc., for like a high degree of accuracy. So check that one out, and I think like people will use that more frequently as time goes on. I think Google's quite good with just creating these like models that have the same sort of information or knowledge about all these different information spaces, right? Like text or images, etc. So check out the Gemini 2 embedding model, just came out yesterday. All right, so okay, so how to decide the ideal chunk size? All right, so I mean, this will really depend on your use case. There's no easy answer for this. As with any sort of like complex engineering problem, like engineers always like saying it depends on the use case. Whenever I say this, like my product manager and my the business folks, the CEO, they hate me for it. But it really depends on the use case. If you're just getting started with, my advice is this: start with something around chunk sizes of around 1,000 or 2,000 tokens. I think this is good for preserving context and like good enough for like whatever use case that you're doing, good enough to get started with. You'll need some sort of chunk overlap, of course, if you don't know about chunk overlap. So if you have, let's say, 3 chunks of 1,000 tokens each, overlap basically means that chunk 1 will contain, let's say, 100 characters of chunk 2. Chunk 2 will contain 100 characters of chunk 1. So there will be like some overlap that happens so that we don't lose information that's on the boundaries of these chunks. So the usual idea is start with like chunk size of 1,000 with like 200 or some token overlap. But what I have started seeing these days is that, again, it completely depends on your use case. For the problems that we have in our toy GitHub repo for this project, for this course, most of the documents that you see in the repo are not really large. And for example, FAQs, an answer to a FAQ might be like 1,000 tokens, might be like 4,000 tokens for some question, might be like 5,000 tokens, etc. Right? So if you're building like some sort of chatbot question answer system only for FAQs, it may make sense for, let's say, if your maximum token size is 2,000 for each document in your FAQ list, then just chunk all of them individually. Don't split them up into different, index all of them individually. Don't split them up into separate chunks, because there is some logical grounding, like some semantic structure already there based on how the documents are organized. One example that I would also give you is that, let's say you're building some sort of complex data analysis AI agent that can look into annual reports for different companies. Now, annual report PDFs are like notoriously big. They're like full of, they might have like hundreds of sections within the PDF. They might have like 20 different sort of financial tables, like balance sheets, cash flow statements, all this sort of thing, right? Let's say you have a balance sheet in there, and the balance sheet is like 5,000 characters, for example, right? And you were doing character-based chunking, assuming, right? So if your limit was 1,000 characters for a chunk, and if you chunk that balance sheet, then within, let's say, the second chunk, there may not be enough information within that chunk to really know that, oh, this is like a balance sheet, right? Like these are the headers of that balance sheet table. These are like the row names. You might lose that information, which is not really useful for your LLM. Once you lose that information, it doesn't know what's retrieved or like what to do with that information. So in those sorts of cases, it may make sense that if you have, if you're building a vector DB of balance sheets of different companies, then per company, one balance sheet will be one chunk. And we can know that a maximum of what a balance sheet size can be like, I don't know, 5,000 tokens or something, right? So there's a lot of like art that goes behind picking the right chunk size. I think of it as like two ways. You have your token-based chunking or sentence-based chunking with like some overlap. And then you have like some sort of structure-based chunking where you already have some structure in your raw data, and then you're sort of like porting over that structure to how your chunks are represented. And like the balance sheet one is one example, right? Like you know that your balance sheet is like one table, so you want to keep it intact. You don't want to like spread it out. So you can think of it as that way. So when it, and like chunk size, again, it's I think one of the most important decisions you make when building a RAG pipelines, because it can have a lot of impact downstream based on like how what sort of problems can be solved there. All right. So again, good question. How to get the count of tokens while chunking? So this is another question that was asked. And you can get the count of tokens by, there are like different libraries that count tokens. The one I use usually, if you're using OpenAI embedding models, like we are in this course, then OpenAI has a open source library called TickToken. So you can use TickToken to quickly like calculate the count of tokens in like any sort of document. So you can integrate TickToken into your ingestion pipeline and do some sort of like dynamic chunking based on, you know, like how big or small based on a number of tokens the document is. All right, let's just answer one more question before we move on. Okay, yeah. This question is about will Databricks replace RAG, as the documents can be directly ingested into PySpark and be queried by using Genie, or we can query with natural language. Is it replacing RAG then? I'm not familiar with Databricks Genie, but I assume that it's some sort of product that allows you to query different data sources using natural language based on the description that you have provided here. So if you think about it, like what is it doing in the backend? It's still doing some sort of RAG. So how Genie is built is still using RAG. So when you ingest documents into PySpark, when you query them, you're still using the retrieval augmented generation workflow, right, in the backend. So you can think of Genie as like it has packaged up like some sort of RAG for you, and you can use it to serve your use cases. So maybe you don't have to build a RAG pipeline yourself. By the way, Google also provides an inbuilt RAG functionality when you start using, I think, the Gemini API. I think the SDK now has some sort of baked-in RAG that using API calls, you can just like upload some documents into the API. It'll create the vector DB in the backend for you, and then you can start asking questions for it. All these tools, they package up RAG for you, and then you can start using it. If it's relevant for you or not, really depends on your use case, your enterprise access, all these sorts of things. If it solves your use case completely with a high degree of accuracy, you don't need to make any major changes to how the RAG pipeline works. And like there are sometimes enterprise and business decisions that also happen there. So yeah, feel free, like use the Gemini RAG or Genie, the Databricks query engine, if you want. But a lot of times what also happens is that you want to make like minor tweaks or minor customizations to your RAG pipeline. It could be the embedding model that you have used. Maybe you find that using the OpenAI clip model, for example, works better for your types of documents. Or maybe you find that, hey, you know what? I would like if I had some sort of query router. We'll see an example of this soon. Maybe I want to make this change, but you really can't because this is a packaged product. You're just using it out of the box. It may allow you to configure it to some extent, but not make wholesale changes. So in that case, you start building something of your own. RAG is a software product. Like RAG is a concept, and you can build software products on top of it. As with any software product, you can either sign up for a SaaS and then start using it, or you can build one in-house. And when you run into problems or customization issues and all, so no differences there, right? So there are quite a few other questions as well. I'll ask these. I'll answer these as we go, and hopefully there's some time by the end of the course to answer most of these. But in the interest of time now, let's go back to our second module, and let's see how we can introduce agentic features in RAG. So basically, like, why do we need to integrate agentic capabilities in RAG? And we saw a taste of that. We got a taste of that in the exercise, right? And we've only built a very simple RAG pipeline for now, but we already saw limitations. So this traditional RAG pipeline follows a very rigid, inflexible sequence of query, retrieve, and generate. There's usually only a single round of retrieval from a predefined source, and there's no ability to refine the search if the first attempt fails, for example, right? So it's really rigid. It's not really flexible. There's also some sort of what I call source selection blindness, which basically means that the system doesn't know which knowledge source is the best for a given question. So if it has multiple knowledge sources, it doesn't know which one to pick from. And we saw an example of this in our in our Jupyter notebook, right? When I asked a query about this Ultrabook Pro charging ports, and it returned troubleshooting information, which was, again, not really relevant as well. While the question may have been about, may have been better answered from the product catalog. So you have source selection blindness, where you don't know which information source is the right one for a given user query. And you're basically treating all queries the same way, regardless of the original intent. So you're not really optimizing the retrieval strategy in this point in time. All right. So in addition to these, there are like other problems that traditional RAG systems might also face. So before we move on, let's do another quick poll. Would like to know like what limitation of RAG everyone has encountered the most frequently. And once we let's just see if some of the problems that you all have encountered can actually be solved by what we cover in the live course. So I'll give everyone a couple of minutes to put in their responses, and then we'll move on after that. Okay, I think we have enough responses. And oh, okay. So the most common problem that we have seen is wrong source selection, and we'll definitely cover one of the techniques that is the most common to fix that problem. And the other problem is for poor document quality. And again, it's a notoriously hard problem to solve. We don't cover it in this course, but I would like you to, because it's an ingestion step problem. But I would like you guys who have faced this poor document quality problem to look into a few things. Look into serialization, which I talked about briefly in the beginning of the course. Serialization basically means trying to sort of transform your raw data into some common format. And I gave the example of how we can have these visualizations like hierarchy charts, right? Like tree, different decision trees, or like stuff like that, like bar charts. I don't know. What you can do is to serialize them, convert them into text. And the text would not be that, hey, this is a bar chart about this with like this points. It would actually be like some sort of like the LLM's understanding of what that visual represents, and it offers you like a more complete representation of something that you can search over. So look into serialization. That's number one. Look into contextual chunking. So contextual chunking, actually contextualization of the chunks. Sorry, contextualization of the chunks means that if you have a chunk of like some text, you create one more piece of metadata, one more piece of text, which is the context about the chunk. It This technique is like it's like front loaded. You're front loading some of the LLM processing there, and what you're basically doing is you pass the chunk, you ask an LLM to contextualize it. Let's take the example of the balance sheet. So if you have a chunk which has like balance sheets, and there can be like lots of rows, lots of columns, maybe some sparse data, maybe not all cells in the tables are filled in the balance sheet. It doesn't really make sense. So what the context of that chunk will be the LLM's sort of understanding, like some sort of metadata that, hey, this is a balance sheet for Apple, for example, for the financial year 2025, right? And it contains like all these things, and it contains this thing, etc. And when you do your search after that, you would do the search both on the actual content as well as the context, the like metadata field about what that context is supposed to represent. So I found that this technique, it's a very simple technique to get started with, to work really, really well, especially with like data quality problems. So you have some low quality data, maybe it's in a completely different language, maybe it has a lot of images, not a lot of like usable things to search on. Try creating some contextual, some context based on your chunk in your documents, and do the search both on the actual content as well as the context of that chunk. And again, that's a good technique to improve the results, right? And then the problem of fixed pipelines, we'll see how to solve this in one of our in the last module actually as well. All right, so we discussed a few solutions that are focused on the ingestion phase. Let's talk about how we can improve things in the inference phase. So what makes a system agentic? Now we talked about the idea of bringing like agentic thinking into RAG pipelines. And before that, we want to know like what means something to be an agent, and it's a very loose term these days. But how I like to think of it as a system can be agentic if there's some sort of like autonomy in decision making in the system. That means that the system can choose the best course of action for a given situation, and it can adapt its behavior based on context, and it can iteratively improve, refining its approach through feedback loops, right? And I saw someone mention this in the attendees chat, so you were absolutely correct that using feedback loops is a big way to improve different sorts of systems, making them more agentic. Of course, this affects agency, latency, and cost, but we're not worrying about that here. So we'll see how all of these things are like all of these approaches are applied to the RAG pipeline in the next couple of hours or so. So using this concept of agentic thinking, agentic systems, these are the exact things that we can add to our RAG pipeline to make it more agentic. And the first one is query analysis. So before the system even tries retrieval, it even runs the query through the vector DB. We can help it understand the nature and complexity of the query. Sorry. And that can mean deciding whether the retrieval is needed or not, right? or which source is the best, like source selection blindness, or what sort of search strategy is appropriate here. I haven't covered it earlier, but when you're doing search, when you're doing information retrieval, you can have like different search algorithms. You can have similarity search, which is most commonly associated with using vector DBs, but you can have keyword search as well. You can have a hybrid search as well. You can have different types of hybrid searches. You can have re-ranking. There are like multiple different combinations of the type of system that you can build, and not all methodologies will be appropriate based on the queries that you're getting. The more surface area of types of queries your RAG system is supposed to answer, the more you need to think about how it can adapt its retrieval approach to make sure that it's getting the right answer back, right? Another example is that if you're working on building this sort of like RAG system in something that's very a specialized domain, let's take the example of like finance, right? Like there might be keywords, there might be like different phrases that are more applicable to finance, and they mean like very specific things than like opposed to like a very generic domain. And in your search system, you might want to make sure that if that keyword means a very specific things, then you want to make sure that the importance or like the emphasis of that keyword is appropriately represented in your search system, right? And that might mean that, okay, maybe you want to use keyword search there, or maybe you want to use a hybrid search where you combine the results of similarity and both similarity search, like semantic search, cosine similarity, as well as keyword search, which can be like TF-IDF or BM25, which is more modern, right? So different capabilities for different mechanisms, and this is why we need query analysis to understand, okay, like for this sort of query, what's appropriate to do here. Second is reasoning and planning, which means that we can break down complex queries into multiple subqueries and try to map out a plan to get the answer. And we'll see an example of that later, and you might sort of be able to understand this problem in one of the issues that we saw in the first Jupyter notebook, which was if we are comparing two products, right? How can we be sure that, I mean, that's a very obvious case for breaking down a big query into like two subqueries, getting the information about both products and then combining them back, right? So reasoning and planning can help there. Third is self-evaluation and reflection, where the system can assess the quality of documents that are retrieved, and it can assess the final answer before finishing up. So this way you can check for any additional processing is necessary. So these are like two different things. We can have this evaluation and reflection happen when we retrieve documents, and we can have it happen when we generate the final output. And these can produce like different sorts of results. And we'll cover both in a bit. Okay. We have this big line here to separate like two approaches. So before we carry on with our study of Agentic RAG, I just want to talk about like a key thing here that's very, very important to be aware of, and maybe even investigate if it's more useful. So you might have seen like either of these as a de facto way of building agentic systems, including Agentic RAG. So one is like building workflows, and one is building like a fully autonomous system. And I have like thoughts about this. This is the third iteration of me teaching this course. And when I started teaching this course almost a year ago, it was what people were building were workflows where you had a lot of control over the different steps that can happen in your whole pipeline, meaning that your LLM is only permitted to take these 5 steps before it finishes up. It can only loop in like some decision points, but not in everything. This used to be the de facto approach of doing things, but like LLMs have become so capable these days that people have almost stopped building workflows, and everyone is building fully autonomous agents now. So an example of this is like agents built using Claude Code. I actually taught a live course on building agents using the Claude Agent SDK, which is a version of fully autonomous. LangGraph, the library that we're covering right now, the framework we're covering right now, is more sort of not suitable, but it's more associated with building workflows like these graphs, right? So I think what I want to mention here is that this applies to Agentic RAG as well. You can either go like fully autonomous, where you give your agent three different retrieval sources. Think of it as MCP servers, or like think of it as skills. Doesn't really matter. Maybe the skill is like getting data from some vector DB. So you can either give your agent access to all the tools and tell it, hey, like I want to answer this query. You have access to my SQL database, the analytics database. You have access to like this set of documents in this vector DB. Now it's your job to figure out the answer and get it back to me. Take as many turns as you need, or do whatever you want, right? So like that's one approach. The approach that we're covering in this course is, hey, we're trying to map out what the agent can do so that we have more autonomy, we have more control, and we don't run into the problem of ballooning costs or latency issues, etc. The thing is that I think the expectations of how these systems are built are changing, but there's still the idea of, you want to be in control of how many tokens, how many dollars you can spend for each query, how many milliseconds your query can take when it fires. Even more so when you're building some sort of B2C application. I saw some like post on Reddit a couple of days ago. There was like the CEO, which was complaining that his AI engineer is saying that the RAG pipeline takes around 20 seconds to run, and it cannot be reduced, right? And he thought that his AI engineer was basically like trying to fool him or like trying to be lazy. But the reality is that there's this push and pull, right? Like, okay, agentic applications do take more time than like traditional software systems that we have been building. But we still want control over them being like really low latency, etc. So building a workflow gives you more control over that, right? And I think both approaches are appropriate for building different sorts of systems. And again, it really depends on your use case. If let's say I'm building an internal tool for my data scientists who want to be able to query all sorts of data, and that is indexed within both a SQL database as well as some sort of analytics system that I have, and also like some sort of document vector DB. And it's an internal tool. Their expectation is just like answer queries or something. I probably would build them a autonomous one because the idea there is like exploration. If it's, let's say, some sort of customer-facing chatbot that I'm building, and this exact problem that we are covering in the course notebooks, where we're expected to answer very quickly. The domain of the problem is quite small. We have complete control over what sort of data sources we have, etc. I think it makes more sense to build a workflow in that case because you can have more control over the latency, the costs, the quality of the outputs, and all these sorts of things. I gave this example last time I did this course, but I work for a venture studio, so we have like different ventures. And what happened in one of the ventures was that the engineer there, he built like this sort of fully autonomous application for RAG actually, but there was like no control over the sort of steps that the agent can take before reaching the output. And what we saw was that within like one day, even with like 100 users for that application, the costs for like the OpenAI API was around $800. And everyone was shocked. They were like, oh, what the hell happened there? And what we saw was that the agent was just carrying on. The LLM was just like, hey, let me check this source. Let me check this source. Let me check like 10 other sources that I have. Let me try to give the best possible answer to my user here, right? So that I'm doing the best for them. But the cost per query was like, I don't know, like $8 or $10. So that is a design decision that, okay, even if you build this and, like you got the right answer in the end, but at what cost? So in those cases, it makes more sense to just, do a workflow where you have more control over these sorts of things. All right. So both approaches are valid. Both of these have their pros and cons. The one that you want will depend, again, as I said, on your use case. So with that being said, let's dive deeper into some of the agentic patterns for RAG. So let's start with query analysis. The purpose here is to understand query intent before executing retrieval. We really want to figure out the optimal approach based on the properties of the query and extract any relevant parameters to try and execute a more targeted search. And using query analysis, our system can decide, does it actually need to retrieve anything? Which source should it use? Should it search using similarity search or keyword matching or like a hybrid method, as I mentioned, right? What sort of filters should be applicable to the results? And there are a few things that you can do once you have analyzed the query. And the classic thing to do is to do some sort of query routing. Let's take a look at this diagram here. So given a query, we can have like some sort of router agent or like router node. Doesn't matter what you call it. But what this node can do is, given the query, try to figure out, should it go to an internal knowledge base or should it go to a web search? So in this example, if it's a question about like financial profile of some company called Acme Corp, it can go to the internal knowledge base, right? But if it's a question about if that company has been involved in recent controversies, this looks like a news question. So in that case, it can go to like a web search node, a web search step, for example. The final step is still the same. It's still some sort of generation, but the knowledge source is different. And we have very cleanly defined based on the query. It can be routed to either of these two. You can have like a third here, doesn't matter. But we're defining like the different data sources and how they are dealt with, even though the final step is still some sort of generation. And there are two main routing strategies. The first one is called single source routing, where we classify the query, send it to just one exact source. And this source can be like a vector DB, it can be an index, it can be some news API or like some sort of other API call, doesn't really matter. It can be a web search API, doesn't matter, but there's just one query, or one index, right? One source. And routing our queries to specific sources reduces noise in the context. And reducing noise means that, we are basically like discarding irrelevant documents, and this can really speed up the rest of the pipeline downstream. The second type of route is a multi-source routing, where we need to send the query to multiple sources. And we can query these sources in parallel to ensure comprehensive coverage of results from like, these different sources. And finally, we merge all the results, and we can either rank them using a re-ranker, filter them out using some sort of other mechanism, etc. But you can see that results are coming from multiple sources. And which one you really use depends on what you're trying to build. One thing that I would like to point out before we move on is I think single source routing is like one way to think about it is that if you have 10 sources, if you want precise control over certain types of queries, then you usually pick single source routing. But if you want more breadth, more sort of flexibility for your pipeline, more flexibility for sort of queries, then you might not have any choice other than using multi-source routing. You may need to search both, do a web search using Tavily or Google, and search for the internal data sources based on, if you receive a multi-hop or complex query. Speaking of multi-hop queries, some queries are just not answerable in one hop. In one step, hop is a step basically, and they basically need to be broken down into subqueries. And this is what we call query decomposition. So the purpose of query decomposition is to break complex queries into subqueries, and then enable our system to route the specific queries to relevant data sources to get more complete set of information, right? And then we can identify any information dependencies between the query, create some sort of execution plan, and then execute the plan that we have, right? And then there are a couple of execution strategies that are typically used once we have broken down queries. And the first one is to execute the subqueries sequentially, where the result of the first subquery is needed in order to do something else with the second subquery. Or you can execute the subqueries in parallel, where all subqueries can be answered independently and you can improve speed. Let's take a look at the visual examples of these two execution approaches. So in this example, you can see that for this query, it's a bit blurry, I know, but for this query, the products launched by Acme Corp in their highest revenue region. So it's a sort of a complex query, right? And you need to, before you can know which products are launched by Acme Corp in the highest revenue region, you want to know what the highest revenue region is. So that's what the first subquery is, which is that region with the most revenue in like financial year 2024. You do like one pass of RAG, you get this result that, okay, Asia Pacific is the region with the highest revenue in this year. And then the second subquery will basically be products launched by Acme Corp in Asia Pacific, right, since this date. And then you get the exact results for the second subquery, and you're able to answer your complex original query in that way. So this is what happens in sequential execution. In parallel execution, what happens is that you might have a very broad query, like compiler due diligence report for Acme Corp. And then you simply break it down into 3 queries. And then what you'll notice about these 3 subqueries that they're like independent from each other. You can ask a summarization of last 3 years of income statement in parallel of like researching like lawsuits, sanctions, etc., in parallel to researching like the organization of Acme Corp, and then combine the results for those in like a final generation step. So since all these are happening in parallel, this goes faster. You don't need to wait for results for one. And the idea here is to make sure that you actually know before you even start executing your query, if it can be broken down and executed in parallel. If it can't, then that's great. And then you can, save on latency. If it can't, like there are dependencies, then you only have, your only option is sequential execution. Okay, and then like one more thing that you can do using query analysis to extract parameters, as I mentioned, right? And sometimes queries contain some implicit information that can be used to make the retrieval sharper, right? So the purpose of parameter extraction is to make sure that we're extracting this additional bits of information that can help with some precise filtering in our search systems based on the metadata of whatever documents we have ingested. Sometimes this technique is also called metadata filtering in different courses, different books. And basically it means that we have like a post-processing step where once we get the results from our query, we like do some sort of filtering. Let's look at an example of this here. So based on this query, show me Q2 financial reports on this, right? So we extract like these sort of parameters, right? We extract that, okay, the time period being searched on in this. Okay, it's looking for financial reports. It's looking for this topics. But if we just like think about this time period, and we know that how we have ingested our documents is each document has like some sort of, each financial document has some sort of like time period metadata associated with it. What we can do is once we retrieve the documents, we can simply filter out the non-relevant ones by only keeping the ones that are relevant to our whatever the query was. And this filtering can happen both pre and post, right? Like I think vector databases allow you to configure if you want to do this filtering pre-retrieval or post-retrieval. Both have their disadvantages and like trade-offs. So like I won't cover that in detail. But basically what you can choose to do, right? Like let's say you want to only look for financial statements in Q2 2023. So if you're doing it pre-retrieval, pre-semantic retrieval, you can do like you can think of it like a SQL-like search where you say show documents where time period is equal to Q2 2023. You get your filtered out documents, then you do semantic search or other types of search over it, right? So there are like different approaches to implement this. But again, this is a function of query analysis. You need to analyze the query and extract parameters before you can do that. And like some common types of things that you can extract is, of course, dates, date, time periods, categories of documents, departments. I gave this example where you have the documents from all these departments, and you want some sort of like access control that engineering documents are not really relevant to like HR. So if HR is using the same RAG chatbots as engineering, then they should only see like HR documents. And metadata filtering is like one way to implement that, right? Okay, so I think we're on the second hour mark. So let's actually take another break before we continue. I think I need to rest my voice as well for a few minutes. And then I'll come back, answer a few more questions, and then we'll continue covering different agentic mechanisms that we can add to our RAG pipeline, and then conclude our second module, in fact, with an example of agentic, router RAG, where we do some sort of query routing based on some query analysis that we do. All right, so since we are halfway through the course, let's take a 10-minute break now. And I'll try to answer some questions in the meantime, and like after I'm back, and then we'll carry on. All right, so see you all in a bit. Okay, so I have been answering a few questions in the Q&A box, but let me answer a few more before we move on. Let's just answer it by sharing with all of you. So, okay, this one is actually the latest question that was asked. So this question says that how can we prepare our ingestion pipeline, is what I assume, right? Like, is there any tool to create good quality data and chunks? Does it make sense to change everything to markdown files, or remove the noise, headers, etc., chunk it after that, and how it works with also? So a lot of questions in that one. And I think like maybe I can help talk about one approaches that like come from one of the most recent projects that I did. So creating good quality chunks, again, like a good quality, like I think the quality that you can get out of your raw data will really depend on your raw data. But like one approach, which is slightly expensive, and I don't know if it's applicable to your exact use case, the person who asked this question, is using another LLM to create the markdown representations. And it doesn't really have to be an LLM. There are different models that allow you to do the sort of like normalization. So let me give you an example. If you have a complex PDF full of like charts, tables, blah, 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 what you can consider doing is calling, okay, what I did in the exact project is call Gemini 2.5 Pro. At that time, that was the latest model. And it had the ability to actually read large PDFs and do things with it, right? Like do some processing. So I used that model to actually create markdown files from those PDFs. And in like a single pass, I asked it to like create the, what do you call it? Like serialization of the different charts and images in that PDF. So the output I got, let's say for a 100-page PDF, now like maybe for some things you cannot do it in one go. You have to like split the PDF into different pages and do it that way. But like the final output was a large markdown file, which is basically the markdown version of the PDF with like some things resolved and serialized. Now what you could choose to do is, depending on your downstream use case, of course you can clean it, you can remove the noise, blah blah blah. Depends what the noise is in your case, depends on what the output of that initial pass was from the LLM. But I like to keep the headers and footers, and for that project I actually created the chunks based on headers. So since it is a markdown, you will have like H1, H2, like 4 or 5 levels of headers, what you have in markdown. And you can then choose that each chunk can be like at the H4, like header 4 level, or it can be at the header 3 level. It'll again depend on the type of use case that you're solving. Once you choose that, you are inherently chunking based on the structure. So I call it structure-based chunking. And from that markdown, I just check like header 4s, and everything in header 4 will be a chunk, right? Like, so you can do it that way. You preserve some sort of like structure around it. You make sure that your chunks are not being split at places where they shouldn't be split at, which was my example for the balance sheet. So if your balance sheet is in a header 4, then it makes sure that, your balance sheet will be one chunk. So you really need to think about what sort of pre-processing you would do that will make sure that your chunks outputs are of your good quality. In some cases, maybe you can remove the header, footers, all other sorts of like semantic structure in your markdown file. or maybe you can use it to make sure that you do more intelligent searching. And then, of course, like once everything is in this like normalized form, like what's the purest normalized form in a RAG pipeline? It's not text, it's actually the embeddings. So if you have picked a good multimodal embedding model, then if your input was like images, audio, and your multimodal embedding model can create embeddings for all of those, then that will be the purest retrieve form. And that will, of course, will be able to be re-ranked, etc. But like it depends on what application that you're building, right? Like for a customer service chatbot, you won't need to return audio files or image files. You maybe just want answers, right? So in that case, it makes sense to convert everything to a text. For audio, maybe you want to create transcripts from it using the Whisper model or something. So again, it all depends. But once you have like this final format, you can of course do all sort of things: search, connect, re-rank, etc. So again, it is a long answer for like lots of questions on that one question, but hopefully I was able to tackle it. So let's do one more before we move on, and then I'll continue answering questions in the meantime. So let's see. Okay, so I like this question. I mean, for people who are getting started, like what's the what do I recommend as a vector store? So again, it depends on what your constraints are. Maybe you want a self-hosted vector store, meaning that you want to host it on your own AWS cloud, or maybe you are fine with using a managed vector store, where you're fine with using a cloud service like Pinecone, which offer their own managed servers, compute, etc. So if it's self-hosted, then you have options like VV8, Quadrant, which offer open source versions that you can self-host. If it's like managed, then Quadrant and VV8 and Pinecone offer like managed vector DB, but you can use them. So that's the first decision. The second decision is like what sort of retrieval pipeline you're building. I ran into an issue when using like it's not an issue. It's like Pinecone is meant, for example, and I don't know the latest. So like if anyone from Pinecone is attending, please forgive me. But like in building one of the RAG pipelines, I wanted to implement like hybrid search on top of it for some use case, and that project was using Pinecone before my time, right? That was the decision that was made. So implementing hybrid search and like how hybrid search works in the backend for any vector DB is that both keyword search and similarity vector embeddings are like different types of embeddings. One is a dense embedding, one is a sparse embedding, and they will need to be stored in different indexes. So in the backend, like you'll have two different indexes, one for keyword, one for let's say embeddings, and then you sort of combine the results when you do your hybrid search using different mechanisms. Like that is some post-processing that happens. Now in Pinecone, you have to like define your different embeddings yourself at that point in time. This is like a problem that I have had like 7 months ago. So you have to like define your own index for a keyword, your own index for that. And then you have to like write your own Python function for combining everything, right? It's not too difficult to do using Claude Code. I think these days you can like ask it and it can do it in one shot. But what I wanted was some simplicity over how these searches are performed. So I started looking at like solutions where I could just, like, I don't want to worry about managing two separate indexes for the same data, just like based on the fact it was storing sparse or dense embeddings or like, for like semantic search or like keyword search. I don't want to handle that. I want the framework to handle that for me. So in that case, there was like VV8 and Quadrant that offer like out of the box solutions where you just like index and like checkbox like enable hybrid search, and then it does that in the backend for you. So your choice of like what I recommend is I really like VV8. I think it's very developer friendly, easy to use. In this course, we use ChromaDB. I think that's one of the easiest to get started with, to play around with, to teach. A lot of people use Pinecone if they want to use pure semantic search and just want completely managed. They don't care about engineer ease of use or like capabilities there, and they can like build whatever they don't have on their own. So it depends. But I recommend this. Try VV8. That's one of my favorite ones. I think it's easiest to get started with. Quadrant I find really good as well. Yeah, so I hope that answered the question. Each will have their own opinions on what sort of functionalities they want to provide. So it depends on what you want to do with it. All right. So since we have covered this, let's move on in the interest of time, and let's see where we were at. So I think we covered parameter extraction examples. All right. So we're still covering like different forms of things we can do after doing query analysis. And I think we covered most of these. So like what's very closely associated to query analysis is the idea of query rewriting. All right. And what we can add to our RAG pipeline is a step where we rewrite a query before searching. And this is useful in cases where the initial query doesn't return the results that your system expected. And you can modify it to, have a better chance of retrieving the relevant documents. And I think I find it useful in like many different, like 2 or 3 different places. So one is, of course, what I just mentioned. We want to rephrase vague queries. Our first search attempt failed. The query, the agent, the like pipeline can be like, hey, let's try searching it for it in a different way. By the way, this is exactly what happens when you use Claude Code or when you use a completely automated agent. If you see it's thinking, and if you have connected it to MCP servers for like searching, it'll try a search. If it doesn't get results back, it'll try the search again after rewriting the query based on like certain feedback it gets. So this is the exact thing that happens, and it has been like coded up and packaged as an agent for us, like by Anthropic and OpenAI, etc. But you can implement query rewriting by yourself, and we will do that actually in the third exercise. But the first purpose is to rephrase vague queries or rephrase queries where you didn't get any results. The second case is adding clarifying context in conversational systems. And this is a classic NLP example. It's called a co-reference resolution. If for those of you who are curious, what happens is that, let's say that you you ask like 2 queries. You ask the first query in a conversational system to like your query and analytics chatbot. First query is that how much was the revenue for Apple in 2023, right? Okay, it returns the answer for you that this was the revenue for Apple. And then the second query you ask is like, okay, where is the headquarters of that company, right? Like, so the second query, where is the headquarters of that company? It doesn't really, like, if you don't have the information that the company you're talking about is Apple, you wouldn't really be able to get any answer if you just pass the second query to your RAG pipeline, right? So that is when you want to add clarifying context, which is basically that you're sort of like resolving different sorts of like that or this or he or she into like exact proper nouns, as I would call it, right? You're adding clarifying context, and query rewriting is the primary way you do that. You can also use it to bridge any sort of semantic gap between user language and document content. We'll see an example of this soon. And the goal is to basically make sure that if, let's say, a user uses, I don't know, a user says YOLO, and for whatever reason, our LLM, or like, not LLM, but like our semantic, embeddings model is not aware about what YOLO is, or the word YOLO doesn't appear in our documents, only the phrase "you only live once" appears in the document, then you want to be able to, make sure that you expand that YOLO abbreviation into its full form. So that's like one place you can use query rewriting in as well. All right, so just to recap, there are like few techniques when we can use when rewriting queries. The first one is expansion. We have contextualization, we have reformulation, and we have step back prompting. Let's take a look at an example of all of these really quickly. So in expansion, we expand a query to add add synonyms, spell out abbreviations like the YOLO example. So if you have this query that Acme is a FX PNL and we want to rewrite it to expand it so that it has a better shot of retrieving relevant documents, right? So you can assign that duty to your query rewriter node, your query rewriter step or agent, if you would call it, right? And then you have contextualization, where this example is actually incorrect. But if your previous query was like, how much did what was Acme Corp's major acquisition since 2020? I think this was, let's say this is the first query. And your second query was, how much did they cost? This is the exact example that I gave, right? Like the co-reference resolution idea, where you want to resolve they to Acme Corp. So again, query rewriter can help with that. Then you have reformulation, where if you ask a vague query, like did Acme buy any startups, you can actually say, this might not result in any, this might not retrieve any results. So maybe let's rewrite it as mergers and acquisitions list by Acme Corp. And maybe that's more relevant to the domain that we're dealing with to retrieve the right answers. Then we have a step back prompting, and this basically refers to abstracting a query to a higher level concept. So let's look at an example. So if you have an original query, which was why was Acme Corp's revenue growth flat in 2025? Okay, how similarity search works is that it's not really like when you run this query through a RAG pipeline, it'll try to retrieve similar documents to this. Why was revenue growth flat, right? And you might not have relevant documents to that exact phrase. What you might have relevant documents is to some idea about different factors that can cause a company's quarterly revenue to stagnate, perhaps, right? Like maybe you search for this on the web or something, I don't know. So what step back prompting does, it takes your original query, which is very specific and maybe doesn't have a shot at answering a question, and it tries to ask a query that's one level higher, more generic, and then it asks both queries to its retrieval sources, and then it answers that query. Again, this is the exact thing that happens when you're using like Claude or ChatGPT, the applications. When in the reasoning traces, what you can see sometimes is that when you ask a question like this, a very specific question, you can think of it as, before I answer this question, maybe I want to answer like the 1 level or 2 level higher question because of that, right? What are the causes of this? What can happen with this? Like if you ask it like, I have a stomach ache, what to do or something, right? Like you can see ChatGPT's reasoning trace sort of like thinking through that, what are the different common diseases that cause stomach ache, for example? And then it asks that question in addition to whatever the specific question was. So this technique is also frequently used in agentic in AI agents and is applicable to agentic RAG as well. Now let's cover reflection, which is another agentic mechanism that lets an AI system look at its own work. And this enables it to evaluate its past actions or outputs, spot any errors or gaps, and then adapt the next steps to improve accuracy. So in the context of agentic RAG, reflection is typically used at two main points. The first one is after retrieval, to assess whether the documents we got are relevant. And the second one is after generation, which is that to check whether the answer that we've been given, which has been generated, is complete and grounded in the sources. So retrieval gives us a few concrete capabilities, right? So we can assess the quality of the retrieved documents by grading documents based on different things. One common way to grade them is based on the relevance to the query. And then we can assess the quality of the response, whether the generated answer is like well supported by the documents or is it complete and all of that, right? And then using reflection, we can run self-correction loops where we iteratively improve outputs by rerunning parts of the workflow based on feedback on the reflection step. And we'll see that we'll see how to do that soon. So this is the example of where we can use the reflection step when grading documents. So let's say our retrieval step retrieves 3 documents, and we can have some sort of evaluation here, and we can use a very, very lightweight model here and do this in parallel. So it adds minimal latency if it does. And then we can say that, if doc2 is not relevant at all, then we just like don't pass doc2 to the generation step. And then we save on some like latency and cost and like reduced noise down the line, right? So this is the first way we use reflection. And when we are assessing the document quality, we sort of look at it in like different ways. So in different dimensions. The first one is through topical relevance, which basically answers the question that does this document address the query subject? The second one is contextual accuracy, that is a document about the exact product, time frame, or scenario that we care about. The third one is completeness, which means that does it have enough detail to answer the question? And finally, we have credibility and temporal relevance, which means that is the source trustworthy or is the information up to date? And again, like which ones you use will depend on what you want to do. for if you're answering like medical questions or something, for example, and you're using a web search API for that. Maybe you want to only use results from like reputed sources and not from like some like my blog post, and I don't know anything about medicine, right? Like that's one example. So the assessment dimensions for judging the quality of the output differ from like judging the quality of the retrieved documents. So when we reflect on generated answers, we're checking the following things. We're checking groundedness, which means are the claims backed up by the retrieved documents? We're checking answer relevance, which means does it actually answer the user's question? And we're checking the completeness of the answer. Does it answer all parts of a multi-part query, right? And there are frameworks like Raga, Students. There are like others that already have some of these metrics built in, so you don't always have to reinvent the wheel to say. And since we're talking about inference time assessment, we can also use LLMs to perform these evaluations. And this technique is also called using LLM as a judge. All right. So through reflection, we can do this approach called adaptive correction. Now we have reflected, we know, like we have evaluated, and we know what the quality of a document or like the final answer is. Now we can use that to adapt our pipeline. We can use that as a feedback mechanism. And the reflection is then essentially a component of a larger pattern here, right? Adaptive correction is the technique which utilizes reflection to recover from poor retrieval or poor generation. We can course correct both within retrieval strategies or have like fallback measures between strategies. This sounds a bit convoluted. I'll show you guys a diagram of what this means exactly. But this basically ensures that we get some sort of reliability in our system. And if we can't guarantee reliability, then at least the system degrades very gracefully, right? So let's take a look at this diagram here. So given some input query, let's say we get some results from the vector DB, and then we have like our document evaluator, and like this can have like one parallel evaluator for like each document. And then based on that, we can say that if, let's say, there were relevant documents in the DB, then we move on to generation and we evaluate our answer and like everything is okay, right? But the other case here is that there were no relevant documents found. Now what we can try to do is we can rewrite our query and try another retrieval. And we can like do this loop, let's say 3 times. And this loop keeps on going on up until like the third try, the LLM is not able to find anything relevant and then it gives up. And then we fail gracefully, perhaps, like we, I don't know, do something else. And I'll show an example of this exact thing. But you can see that the main thing to point out here is there's 2 loops here where we are incorporating feedback. So we're first trying to rewrite the query if we don't get any relevant documents. But the second loop is this one, right? Like where we evaluate our answer. So if the answer is relevant, then we're all good, we're all done. But if the answer is not relevant, then we sort of try to rewrite the query and try this whole pipeline again. So the second loop is this one. So one thing to note when you're implementing like this reflection and cyclic mechanisms in your Agentic RAG workflows is to make sure to have a maximum number of iterations, or you'll run into the problem that I mentioned where, you know, your agent can keep on going on and not get any relevant results, but add to your latency and total cost of running problematic queries. All right. So, which is why you should care about termination conditions. You, of course, need to know when to stop the correction loops. And the obvious one is that when you reach some sort of quality threshold, then you know that you have to stop, and this is your success criteria. This is your base case. Or if you hit some maximum number of iterations, and this sort of means that, okay, you reached an effort limit and you should not proceed because, you know, you don't want to keep doing the same thing again. Or you may choose to terminate when all fallback strategies have been also exhausted. So this is like a graceful execution, a graceful failure pattern, where you try like 3 different knowledge sources for something, and then if none of them retrieve any results, you can gracefully say that I don't know what the final result is, right? And what I recommend as the approach is to think of it think of adaptive correction in 2 tiers. The first one is self-correction loops, And you can use these to iteratively refine within the same strategy. So when I say strategy, I mean like one route in a agentic RAG workflow. So this can mean like refining the query based on quality feedback, adjusting any filters, or retrying the same source. Tier 2 is what I call fallback mechanisms. And if your self-correction doesn't work, then you can switch between different strategies. And that could mean trying a different knowledge source, or changing the retrieval method, or escalating to external sources, or even a human if your use case calls for it. So for example, like one of the ventures that I was supporting, they built an agentic RAG pipeline where we had a workflow with some self-correction loops for query rewriting. But if it failed to find relevant documents more than once, it would call a web search API to try and retrieve the relevant data, right? So you can have like, this is like a post routing, you can think of it. So instead of routing upfront, instead of saying that, hey, like this query looks like a web search query, I'll just directly hit web search. What you can also do, depending on your use case, is you try to retrieve data from your internal sources, because perhaps those are your source of your utmost truth. But your graceful failure mode is that, hey, like if I can't find anything in my internal knowledge base, then maybe I hit a web search and try to find the relevant data, right? So it depends on what you're trying to do, but there are like multiple ways to do this. So we've got a lot of agentic RAG patterns. At this point, I just want to know if any of you have tried any in your agentic, in your RAG workflows already, and if so, which one? So I'll give you guys a few minutes, and you can put in your responses to the poll, and then we'll proceed. We have enough responses. I was also answering a long question in the Q&A box. I think quite an interesting question about building an on-premise RAG pipeline. So I think there are a few ways to do it, but it's a long answer, so I think everyone can check it out. But yeah, let's see what everyone says, right? So I think all of you have, like more than half of you who have responded have tried query routing, but not a lot of you have tried query decomposition, which I think is the most complex pattern that we will learn today. All right, so, but there's a chance to do that in this course. So let's see, in the interest of time, actually, okay, I have this section in the course that talks about like the setup of the problem, right? That we're doing agentic RAG for like Techmark, it's an e-commerce website, and what are the data sources, 3 data sources, etc. But I think it's missing this one. But we're simply talking about the different failure modes, etc. And I think we saw these when we ran the first notebook. So I think in the interest of time, I will not cover this set of slides. It basically talks about the different examples of failure modes. Maybe very briefly just recap. So you can route to the wrong source. We saw this example here, right? You can also have poor document quality. And this might mean that your results are polluted and the LLM is not able to generate an appropriate response. And the third failure mode was that you can have multi-hop queries that need to be decomposed, and you're not able to do that because your RAG pipeline doesn't support it, right? You'll have to build something more complicated. So we'll cover that, all of that in a bit. All right, and then just before we go on and build our query routing RAG pipeline, just some notes about like different choices of frameworks that you could use to build Agentic RAG. So the first one is, and what we're covering in this course is LangGraph, right? It's a very low-level framework. Everything is decomposed into nodes and edges. It's graph-based. You can build your own graphs, including like decision tree type of graph cycle. There's a global state that flows through node to node, and it can be defined. We covered all this. The other option that I did not cover is LlamaIndex, and it's a data-centric framework. And I think it's quite optimized for rapid RAG prototyping, and it offers an event-driven pattern for workflow orchestration. You can define workflows, and you can define like sort of like pseudo graph-like structures there, but it actually works by using type annotations to trigger different nodes, right? So like based on the return type that you define when you're defining your LlamaIndex workflow, you can trigger like different nodes. And I find that to be like, I personally find that to be a bit more complex than using LangGraph. So that's why I chose LangGraph for this course, not covering it in detail. But the main idea is that there will be always like many frameworks, right? I don't think it's important to argue between LangGraph or LangChain or LlamaIndex or talk about frameworks all day. What's more important is that the principles, the design patterns matter more than the framework that you're using. I think you should just use a framework that you're comfortable with, or the one that offers the most baked in functionality for your use case. If you want to build a very, very simple RAG pipeline and it works for your use case, then sure, use LlamaIndex or sure, use LangChains. They have their RAG wrappers as well. But maybe you want to build a complex RAG pipeline because you encountered the same failure modes that we saw in our first notebook, then maybe you want to use LangGraph, right? So again, or maybe you just want to use Python without any framework. So the design patterns of how these agentic RAG things are structured is more important than the choice of any framework. The other thing is that these frameworks can be combined as well if you want. Maybe you have a retrieval agent node. You have like 3 nodes, right? And if this is the retriever node, then like it can actually have like LlamaIndex code here. You don't need to use, you're free to choose what to do within a node. It's just a Python function. It can use whatever framework inside the node. So feel free to like combine and mix and match if you want. So that's why don't get too hung up on which framework or this framework or that framework. Focus on the foundations, focus on the principles, and try to match the use case with like design patterns, and then try to see what framework gives you the capability to implement that. If none of those do, then just use pure Python. With that being said, I think it's time to look into how to actually build a single agent RAG, like using a query router in LangGraph. And knowing how to do that will enable us to understand like how to build more complex stuff. So let me just share my screen. I'll turn off my video so the bandwidth doesn't complain this time as well. And I'll just cover, we'll go over the query router example. So sharing my screen now. Okay, let's go with the second load. All right, I think everyone can see the screen now. Again, please, as I mentioned earlier, I implore you all to, when you're done with the course, use your favorite coding agent, go through the notebooks, try to fill in the gaps in your knowledge. What's more important is the design patterns and how we design the workflows. What's not important is the like what imports we use, etc. Right? So don't worry about that. So this notebook, the second notebook of this course, will build the agentic RAG using a query router. So we started our imports. We started with our environment setup as we did in the last exercise. One additional thing we'll do here is that we're using Tavily as well, as you see in the API. So Tavily, as I mentioned, is a web search web search for LLMs is how they market it. There are like plenty others as well. We're using Tavily because they give like enough free credits. And once you have the key from Tavily, you can start using it to do web searches within your code. And the results will be optimized for like LLM sort of generation use cases, right? So you can think of RAG, or you can think of Tavily as like RAG, but connected to web search, right? And what we do in this setup is that unlike our basic RAG notebook, we have three separate ChromaDB collections. So, remember the notion of three different tables for different types of data? That's what we have done here. So one of the problems in our first setup was that all the data that we had was all this catalog FAQ troubleshooting was all indexed into one single vector DB index, one single table. So there was no way to sort of make sure that, hey, like this query should only go to FAQ. So to solve that problem, how we've set up this notebook is that we have three separate ChromaDB collections. And I saw some guy asking about how is the RAG connected to the data. Please go through the README. This has setup instructions, and this has instructions on how to set up the vector databases. You'll find your answer here, right? So I don't want to spend time covering it again. Okay, so now that we have set up if you run the scripts, you'll have this baked in, and the focus here is how to use this once you've set it up. So now that you have the three indexes, you need to connect to each collection separately. Let's minimize that. So you need to connect to each collection separately. So in basic RAG, we had, let's scroll up, quickly compare. So we had one vector store, we defined it like this. We take the same approach here of defining the vector store, but we define three different ones, right? Like one for catalog, one for FAQ, one for troubleshooting. The mechanisms of how to do this are exactly the same. They use the same embedding model, but they're just like represented by three different objects now. And then we can see that each collection has like different number of documents based on their type. And if we run this cell, we'll be able to like run different queries and then, like get data. So you can see that for this query, laptop with good performance. By the way, we're like specifically mentioning which database it should go to, at least in this test cell. So this query, we are only sending it to catalog collection, and then we can see only catalog results are obviously returned, right? Like, okay, because we have programmed it that way. Now that all this is set up, we can see that, okay, if we pass in the name of the vector DB to query, name of this, don't think of a vector DB, like name of the index to query, name of the table to query, then we'll be able to sort of like isolate our queries to like the right source, try to solve this source selection blindness, right? So we're all set up in the different vector DBs. We just initialize our models now. And at this point, what you can do is, I've been lazy. I just use GPT 5.1 for everything. But now that we have started using different LLMs for different things, like one for generating an answer, one for routing, making like routing decisions, like when in our query analysis, the query analysis will actually be done by an LLM, right? So once we start adding different points in our workflow where an LLM needs to be called, we have a different decision that needs to be made, which is that which LLM should be called for this, right? So you can choose to use your own internal open source LLM or a very like small LLM, like, I don't know, 5.1 nano or something for routing. And you can choose to use a different, stronger LLM for the actual generation. That's completely fine. And then, you can start optimizing latency and cost as well. So if you use a smaller model for this one, a more complex, larger model for this one, then you start like optimizing your workflow. For this example, we're just going to be lazy and just use the same one. And then once your workflow starts maturing, your schema also starts maturing, right? So I hope a lot of you are aware of the concept of getting structured outputs from LLMs. And that basically means that if, let's say, we want our LLM's output to be in very crudely saying like a JSON or like a Python dictionary with like two fields, the chosen collection and reasoning, then we can define like the schema for the output for that LLM. So what we're defining here basically is that when we call the LLM to make a routing decision, then its output should have two keys. One is the chosen collection, and it can be like a enum of like only like these types: catalog, FAQ, etc. And then the other attribute can be like reasoning, right? Which can basically be okay, explanation of why this collection was chosen. By the way, it's been shown that if you ask an LLM to provide reasoning when making decisions like these, it performs better. So that's what we go with here. And then what we'll do with that is that we create a chat prompt template. We did this for the generation step, but since we're making another LLM call here, we need a prompt template for that. And in this prompt template, we pass in some instructions. We pass in instructions about what collections are available, what query we have, and like how routing should be made, and like some few short examples that if let's say someone is asking for a laptop recommendation, then it should go to the caps log. If someone is asking that, saying that their laptop won't turn on, then it's troubleshooting. Not always necessary for larger models, but can be quite efficient for smaller models, these few short examples, right? And then we create a chain. So this is a LangChain concept. Not important to dive deep into this, but basically this means that given some input to the chain, we'll first like invoke the prompt like we did, right? And this will give us the final string, which has the query put in, the query hydrated, and then it'll pass it to the user like this, like a pipe, like bash script. So you can pass it to the LLM, and this LLM will basically will invoke the this LLM object will invoke the model endpoint, and this with structured output method allows you to quickly define like what schema you want your output in, right? So in our router output, we defined it above. We said that we want the chosen collection reasoning, and then when you pass in this to method, whenever you invoke the router chain, it will always contain this structure. So let me show you an example of what I'm saying. So for like this test query, tell me about an ultrabook battery. We invoke it to the router chain, and we simply get the result back. And then you can see that we're accessing the attributes of the result, right? The chosen collection and reason. So what you get is the object of the router schema back, and it will have these two attributes filled in. And then we can see that for this query, we see like which collection was resolved by the LLM and what the reasoning behind that was, right? So this is the importance of structured output, that it allows you to like bound your output to like some sort of schema. So now we have added one more thing, actually a couple more things to our state. So we had query earlier, we had the list of retrieved documents earlier, we had the answer earlier, but we've added the chosen collection and the routing reasoning to our state as well, right? But everything else is the same. And then we create, we have the same retrieve node, we have the same other nodes with like some slight differences. But this is a new node we have, which is the router node, which does the query routing for us. And as nodes are like Python functions, what this function does is it gets the query from the state, it invokes the chain, it gets some result, it gets a chosen collection and a reasoning. We're just like logging it, printing it here. And then we update our schema with the outputs of like, the router result. And we update like these two attributes. So these will be updated on our state. And then we're creating actually four different retrieve nodes here. So we're initializing a Tavily retriever. Again, not super important. This is basically an object of the Tavily search API. We pass in our key, we pass in the number of search results, some like parameters to say that, hey, we don't want the generated answer, we don't want raw content. We'll use it soon. And then similar to how we defined like one retrieval node in basic RAG, which was here, right? So we had this retrieve node, and this worked for like one vector DB collection. Since we have 3 collections now, we keep things simple and define like 3 retrieval nodes. And these are exactly the same as the one here. It's just based on what collection we're hitting. So the retrieve from fact node will only hit the retrieve from FAQ will only hit the FAQ store. Okay, so, and then we define one more retrieval node for the web search. And then we have a final generate node, which is exactly the same as the basic RAG exercise. There's absolutely no difference here. And then what's different is that we need some sort of routing. And routing, like making a choice between which node should be executed next, is done by using conditional edges in LangGraph. So as we mentioned, right, like LangGraph has simple edges, like just one node to another node, and then conditional edges, which is basically like one to many, right? And what this node takes is a routing function, and then like some sort of way to decide some sort of way to decide which collection is called. So let's just ignore this for now. Let's look at how the graph is built. So we add the router node. This here we're just like adding all the nodes to our graph object, right? So we add the router node, we add all the retrieve nodes, the 4 retrieve nodes, the generate node. Okay, all done. We set the entry point, which is the router node. Okay, this is a new node that we have, and then we add a conditional edge. So by the way, the router node is what we defined here, right? Like the query router function, which calls the router chain, and we basically then start defining our conditional edge, which will take like 3 things. It'll take the origin node, which is the router. It'll take the routing function, and then it'll take a map, a dictionary of based on the output of the routing function, which is the next node to call. This looks a bit repetitive here, but I think it's important to just break this down. So this is the routing function, and routing function is basically something that basically decides based on some input, it gives you some output, right? And it's very simple here. So this routing function, it checks the state. It gets the chosen collection from the state, which was returned by the LLM. And then it returns like this string, which is like retrieve blah, right? And then you can see here that based on the output of retrieve catalog, we call this retrieve catalog node. So this is the key is the output of this. The value is the name of the node, right? Which is this. And it looks a bit convoluted. I think it's because of how the schema needs to be defined and all. But this is the most complicated part here. Everything else is simple. We just like add the other pending nodes. So all the retrieval nodes are connected to the generate node, and generate node is connected to the end node. So this is a lot of code, but it looks pretty simple if we visualize it, which you can do in LangGraph, right? So given the start node is connected to the router node, this is the start point. All these dashed edges are the conditional edges. So based on some router, or based on the output of the router, it can either go to one of these 4 retrieve nodes, and all of these will be connected back to the generate node. All right. And that's it. This is what the graph is doing. The only complicated part is just defining this conditional edge, which is basically, again, like these are all your, based on like the output of this simple function, these are the name of the 4 nodes that should be connected to. And this is the possible output of this function, and you get this. So once we have defined our router RAG, we can start running some queries. So for example, for this query, what I need a lightweight laptop for my university. What do you recommend? It says that, okay, the user is looking for this. This is the reasoning. It made the decision that it should be routed to the catalog vector DB collection. And then you can see all the results are from the collection, catalog collection, right? None of these are from troubleshooting or whatnot. And we get a nice answer here. So these are all like examples that work well. Let's look at an example that didn't work well in basic RAG. So we asked this query, Ultrabook Pro charging ports. Now what we are able to do is that, given this query, the LLM decided that, okay, it should go to the catalog, okay? And since it goes to the catalog, you can see that it retrieves all these documents. What's interesting here is that it actually was able to retrieve the product spec of the Ultrabook Pro 14, which perhaps is what we're looking for. And then you can see that the generated answer is that, hey, the Ultrabook Pro 14 has 2 Thunderbolt ports for based on USB-C. So this is already an improvement from the last basic RAG thing, where we were not able to answer this question at all, right? Because it was deemed vague. Another example is that if we ask about the return policy, this no longer returns monitors, right? Where this answer is obviously about some sort of return policy. We're not asking for what monitors we have. while if you see if we just quickly scroll down here, we asked about the monitors. Let's see, where was it? Yeah, so when we asked about the return policy for monitors in our simple RAG pipeline, you can see like a lot of catalog monitors being returned from the catalog, right? Which is completely irrelevant here. So again, we've solved the second problem as well, that, hey, we're not getting data from the wrong source. And it actually works well that, hey, most products at TechMart do this. It's quite well, right? Like while here you can see that there's a lot of noise. So, and then the third case is that, let's say if we ask a question that doesn't have any information in our DB. So like in our vector DB, there's no document that answers how to solve this Windows 11 error. It can say that, hey, the query should go to a web search actually, and then it can get like these documents back from Tavily, and then it can like answer that question well as well, right? So maybe you want some case in your RAG workflow where it is able to do web searches for answers that are not there in the vector DB. So you answer that question as well. But there will still be some problems here. I mean, we solved some of the issues from basic RAG, but there are still like challenges around multi-hop queries, and like sometimes like within a collection, there might be still noisy documents. So we'll try to solve all these problems in the last implementation when we implement our agentic adaptive RAG, which will be if I were to give you a taste, which will be a super complicated looking workflow. But I'll break this down when we come to it. And I think it's important to sort of cover the concepts behind this before we start implementing this in code. So yeah, we're at the end of our third hour here. Let's take another 5-minute break, I think. And then when we come back, I'll start covering the rest of the material, basically how to combine everything we have learned into building something like this here. All right. So let's stop sharing and okay. All right. So see you all back in 5 minutes. All right, so we have around about 50 minutes left. So yeah, in the interest of time, I've answered a couple of questions in the Q&A box, but in the interest of time, I'll go through covering the material first before seeing if there's more time to answer the remaining questions, because I think we're now getting to the part where we implement some really, really complicated things here. So with that being said, let's move on. So yeah, so we've already seen this, how we can use LangGraph for agentic RAG. This is a short section about how, like if we have nodes, which can be like different agentic steps that you take. You can have a different node for query router. You can have different nodes for, let's say, evaluation here. So LangGraph is a good choice to represent those sorts of processes. And then if you have like routing decisions, not query router routing, but like if you have like decisions about which is the next node to be executed, then you have conditional edges to implement those as well, right? And then for any sort of like adaptive workflow, you can implement them using self-correction loops. And this we already covered as well. So I'll just skip over a couple of slides here in the interest of time, and just talk about like the best practices for designing agentic RAG workflows or any sort of like agentic workflow. So I like to think of designing agentic RAG workflows or like agentic workflows as building with Lego. The patterns that we have talked about, like query routing, reflection, query decomposition, these are our Lego bricks. And real applications, in my experience, they almost like very rarely map one-to-one to like one single pattern. And you usually need to like combine multiple of these patterns, multiple of these Lego bricks to actually build your final system. And you might need to combine them in like different sequences or like different numbers of those, depending on your use case, right? So the process that I recommend when designing your workflow is this. First, you have to deconstruct your user needs. This means identifying the type of queries that you expect and think about what's a good output for different query types. One thing that's important here is that, again, all the code I've shown you, like Claude Code can write it, like Cursor can write it, right? Like there's nothing special in writing code these days, but what's important is that knowing the system that you have designed is that solves your particular use case, right? So I think like more effort should go into like designing, like planning before any of the code is even written, right? So yeah, deconstruct your user needs, try to figure out what sort of queries they will ask and like what is a good output for those queries, and then try to map those queries, that those like categories of queries, to like different sub problems that can be solved, right? If you find that there are lots of categories of queries and you need to pick between different sources, then you can use query routing. If your queries are complex, then you can use query decomposition. If there are quality concerns, then you can like add a reflection step, right? So with that all in mind, you then need to sketch your flow and decide which nodes are needed, in what order, and what we might like where we might need to add branches or loops in our workflow. And then let's also skip over, I think, these slides. I think this covers most of what I wanted to say about designing agentic RAG workflows. So feel free to look at this material in the slides in your own time. Let me move on to more practical aspects, right? So two of the most common architectures that you can build using that like are covered in agentic RAG are corrective and adaptive RAG. So corrective RAG is basically there are situations, and there will be many situations, where irrelevant document chunks are retrieved in the retrieval step, no matter like what quality of search algorithm that you write or like the scoring that you use. There can still be irrelevant documents that are retrieved, and this can distract your LLM, leading to incorrect or hallucinatory outputs, right? And corrective RAG addresses this by self-correcting retrieved knowledge before like giving the documents to a generation step. And we basically include some sort of lightweight evaluation agent that assesses the relevance of documents for a given query and assigns some sort of confidence score. So we've seen this in practice before. I covered this in the last couple of hours, where we have this sort of like query. We have like two places where evaluation is happening for the documents and then for the final answer. And this is like the essential like nature of corrective RAG. Even before you generate like an output, there's some sort of like quality checks, some sort of correction and like feedback loop happening before we even go to generation, right? And this is like the idea of corrective RAG. You add different corrective steps in your agentic RAG workflow, and here we've added 2 steps. And the other idea is adaptive RAG, and this is more of a philosophy rather than like one single technique. And if you read like a research paper, if you take another course, you read a book, then all of these will have a different variation of the same philosophy of what is an adaptive RAG workflow. What I like to think of it as, adaptive RAG is like a state of mind. It's like a single workflow cannot efficiently handle a vast spectrum of user queries. It's not really possible. So you compose multiple patterns into some sort of dynamic system that allows the LLM, that allows it to self-select the most efficient path for each query, right? And the common way it's built is that there is some sort of query router at the entry point of adaptive RAG workflows, and then there can be like multiple paths. So in this example, there can be like a direct path, meaning that there's no RAG response needed. There can be a path where, okay, there's like RAG with some sort of corrective loop inside it. Or maybe there's some RAG with like external sources, and then there's some like fallback and retry mechanisms before query rewriting. Yeah, this doesn't really make sense perhaps, but let's try to visualize it and see what one adaptive RAG, what a adaptive RAG workflow could look like, right? So you start with some query router, and then you have like different paths. So let's say that one of the paths is this one. So based on the router, we decide that, oh, okay, we don't actually need to retrieve any data from our documents. This can be answered by my own knowledge. This can be answered by my own training weights. If someone asks what is Python, for example, right, you don't need to like look at Python documentation, and LLM can easily answer that without looking up information. So for these sorts of questions, you can just directly generate a response and you finish. That's it, right? Another path can be that, hey, I need to do some web search. Okay, that's fine. Another path can be that, hey, I need to look at one of my or multiple of my internal vector DB indexes, right? Okay, fine. So once you retrieve from these different data sources, you can then have the same process where we grade different documents, like the corrective loop, corrective RAG pattern comes in here. So based on the grading of those documents, if you find something relevant, then awesome, generate the output. If you don't find anything relevant, then there's this like sort of decision that, hey, did you reach the retry limit? And did you reach the termination condition, or no, not really? So at that point in time, you decide that, okay, maybe I need to rewrite my query. You rewrite your query, and then you do the same loop all over again here. What we will build in I don't mention query decomposition here. So this assumption is that this whole is for a single query, right? But this whole graph is for a single query. But what can also happen is that you get a complex query, you decide to break it down into subqueries, and at that point in time, you can then call this graph for each of the subqueries sequentially or in parallel. And then you again, based on your requirements, you get this like really robust and in some cases reliable system where you have very good fallback mechanisms. You have like very good different options that are being routed to. You have like grading happening, etc. And this is how I think like a lot of the production RAG systems will have to be built, right? Like you're basically importing a lot of system design principles about like fallback, about circuit breaking and all, in building like retrieval and retrieval augmented generation pipelines here as well, right? So that's the same idea. How can you build like a system that, based on your requirements, based on your constraints, can handle different edge cases? And if it doesn't, then how does it fall? How does it do fallback? How does it fail gracefully, etc. Right? So, the major challenges and like strategies you start facing, and someone already mentioned it. I see a couple of people mentioned in the chat and the Q&A. Is that, oh, what about latency and performance, right? Like, what happens with those? And I answered the question just now during the break about this. So yes, it's true that multi-step workflows, of course, 100% introduce latency, and in some cases it can be significant. But it's a very intentional trade-off that you're making here, based on, do you value latency in your use case, or do you value like accuracy? Do you value consistency of the answers, or do you value like, should there be more true positives, or should there be more, what happens if there are like false negatives or false positives? Like, which one do you want to avoid, etc. So it depends on those, but like, still there are some sort of mitigation strategies that you can look at implementing to take the sting out of the latency and cost effects of having multiple LLM calls within one workflow, right? And then the simplest one is, of course, caching. So you can cache frequent queries to avoid redundant computations. And caching can be actually done in multiple places. So if, let's say, you have some cache here, right? And let's say this is the cache. And if you have a query coming in and it hits your cache, it meets the requirements, then instead of it running through all of this, you can just return the final answer here, right? So like that can be like one place that you do your caching. Another place where you can cache is query routing. And let's say like you might ask, like, in what sort of situation might you want to cache in this place instead of here, right? Because like if you have a query coming in, then you don't even reach that place. But what can happen in the case of, let's say, queries for news or recent events is that you have a query coming in and you know it wants to go, it needs to go to a web search, but it's a query about a recent event. So the cache invalidation strategy will be that the cache has a small time to live because news can change. But the query that comes in, you still know it has to go to a web search. You still know it has to go to a web search API, a news API, right? So instead of caching the final answer, you can cache at the router. That query comes in, you know it has to go to a web search API. Awesome. You don't need an LLM to tell you that. You directly go to this web search thing, right? And then you save on latency there. So the idea behind this is that you can have your overall cache, yes, but this will have like different cache validation strategies. And then you can implement like caching at like different levels in your LLM API calls or routers, etc. And again, it'll really depend on what you're trying to do. So always like think about caching as like the first mitigation strategy and like different levels where you can add the caching at. The other strategy is to always try parallelizing whenever possible. You should implement independent workflows in parallel whenever you can, and this will always improve the throughput. Your latency will basically be the latency of the slowest query that runs in parallel. And that's why in your query analysis step, you should always try to like figure out if you're dealing with like some sort of multi-hop query or complex query that needs to be decomposed. Is it possible to run it in parallel or not? Of course, I mentioned this before, but you can use smaller language models like Claude Haiku or like Gemini Flash for different steps. Perhaps for not generating a final answer, just for routing, you use a Haiku. Or you consider like fine-tuning your own very small models. Like I think like models like SBERT, etc., work very well for query classification. And in your router, if you already know what your data set is and you can train your own model, this will take like 10 milliseconds or something to run on your like hardware that is optimized for it, right? You don't need to call an LLM to do query routing. So this like completely takes out the like bottleneck from there. So the main point is that when you have more complex workflows, you have to make more decisions about which LLM, what cache strategy, etc. But then there's like opportunities as well in those decisions to like really optimize for your latency. All right, and wherever possible, try to optimize search algorithms if your retrieval is slow. So one example can be that for some sort of queries in your query analysis, you probably figure out that this should go to a keyword search. So if that is the case, then simply run the query on keyword search. Don't make it go through semantic search. Keyword search is much faster than semantic search. And then you try to like optimize your latency that way, right? One very useful way to just reduce latency in any sort of AI or LLM application is to control the LLM output length. The latency is directly proportional to the length of the output. If it takes more tokens to generate, then it'll take more, the latency will obviously be more. So always ask for like outputs that are as small as possible using structured outputs. So if it's a query routing decision that needs to be made, just like ask for the smallest possible output. If you are judging the grade of retrieved documents, then just get like a binary yes or no. Is this document relevant or not in your, reflection corrective RAG step? Don't ask for the whole generation. Don't ask for the whole document to be generated back. One of the one of the common mistakes I've seen people made in like many projects, number of different projects, is that in this corrective RAG step, what people do is that they pass it to LLM. They pass like 10 documents and ask the LLM, hey, can you return all the relevant document back in the final output, even if it's a structured output? No, please don't do that. What you should do instead is if you have 10 documents, 10 LLM calls, you're just asking the LLM to give you a binary yes or no back, like if it's relevant or not, right? First of all, it'll be super fast because you're not asking the LLM to generate all of the outputs. The second thing is that since you're parallelizing it, that also saves on the latency a lot. So there are a lot of design decisions that you can make in order to solve the different problems that can happen here. So always be mindful of how you're designing your workflow, right? Then we have challenges associated with cost management. And I think a lot of these are really similar to the strategies in mitigating the latency, and like both sort of work hand in hand, at least in terms of LLM and AI-based applications. But obviously, yeah, number of LLM calls obviously directly proportional to the operational cost. So try to design your workflows intelligently, meaning that try to have paths that avoid complex operations. So if there's no RAG needed for a system for certain queries, then don't do RAG. Like don't generate a response from documents. Just let the LLM answer it. And we had that in our workflow that I showed in the example, right? Like the direct response generation. The second one is that, yeah, you can choose the right model for the job. You can try to balance capability, performance, and cost, etc. And this will save on your latency as well. And then, of course, try to create concise prompts, as concise as possible. Try to create control the output length. LLM costs, all of you know that output tokens are charged higher, maybe like sometimes 10 times higher than input tokens. So this is really the thing you should be optimizing for always in your LLM applications, including RAG. And then we have like some strategies for debugging and observability. So the dynamic nature of agentic RAG workflows can make debugging difficult, of course, right? Like there are many paths the LLM can take, etc. You don't know, it can be hard to build a logging system around it. And I'll actually show an example in the exercise. But yeah, it can be hard to build a logging system for agentic RAG workflows where things can happen in parallel, things can change dynamically. So in these cases, if your system allows for it, if your company allows for it, use observability platforms where possible. Use like LangSmith. LangSmith is a paid one, it's proprietary, but there's an open source option called LangFuse. Try to use that. There's like plenty of LLM workflow visualization frameworks these days. A lot of them are open source. Please use them. Don't reinvent the wheel. Don't build your own logging system. It's a nightmare if you have to build that. Make sure that whatever framework you choose can capture everything, right? The input, output, state changes, etc. in a workflow. And a lot of these systems like LangFuse is pretty customizable, I think. You can use Python decorators to sort of like manage what's being logged and what's not being logged, etc. And try to set up some sort of, try to set up some sort of alerts or real-time monitoring to notify yourself of anomalies, performance degradation. These are all like super obvious, super basic systems design principles. There's nothing really specific to RAG here, but these can be applied as well in agentic RAG systems. The other thing is that for more complex workflows, errors in a single step can and will propagate throughout, and they will lead to incorrect final output. So if you make a wrong choice in the query router, yeah, like whatever you do after that doesn't really matter, right? So unless you're doing some sort of adaptive correction, making the right choice after that. But like the idea would be to try and figure out what problem happens in the router itself, right? So obviously you can build in self-correction. It's a core feature of agentic RAG. There will be fallback, there will be unexpected behaviors, graceful failures, etc. But try to like make sure that you can improve, self-improve, self-correct. And I don't mean like reinforcement learning or anything. These days, like tools like OpenClaw, Claude Code, what they do is that they sort of capture the mistakes they made, the like things, etc., like mistakes, let's say, in memory, right? Like there's like a memory.markdown file, which is basically like a way to organize the system prompt, right? So what you could do really is that, and I implemented this in one project, is that let's say you make a wrong decision in the query router, and you're able to identify through LangFuse or LangSmith that, okay, yeah, this like this input output pair was not really correct. There can be a way in the query router system prompt to have like a dynamic list of past mistakes, okay? And whenever, let's say, a human reviews in LangFuse, or maybe like you don't need a human review these days, but the idea is that whenever you make a mistake and you realize it, the agent can realize it on its own, or a human says that, okay, it flags the mistake, then you can dynamically update the system prompt for your query router using the same, it's a memory management mechanism, so that the query router adds that as like a few short example for later and doesn't make the same mistake again. So try to use those approaches for error handling. You can use your adaptive correction, of course, but this is another way of incorporating things where mistakes are made frequently, so that you don't rely on the fallback mechanisms later. You preemptively catch your past mistakes and you learn from them on your own. All right, and then there are some considerations that you need to make when moving to production. So of course you can do this in a prototype, but like moving to a production system requires a careful planning across the full agent ops, as I like to call it, lifecycle. And basically, there are like some best practices that I just want to mention. So the first one is that try to design shallow workflows as possible. Don't try to minimize the number of hops. You can design really deep workflows to like make them really robust, but it'll of course add to your latency, and it can become a nightmare to debug in the future. So when you're designing your workflow, try to keep it as shallow as possible, right? And again, like that's why I sort of keep on emphasizing that Cloud Code can write all of your code for your workflow. But sometimes if you ask it that, hey, make sure that this problem doesn't happen, it can like add a node it can add a layer of depth in your workflow. And okay, it probably solves the problem, but then you have the trade-off of cost and latency, right? So the design is something that you should still be very mindful about. Try to use eval-driven development. So make sure that your development process works on a continuous cycle of evals, and have like evals for every specific step of your agentic RAG workflow. And a lot of like evaluation principles of information retrieval and LLM applications apply here. We didn't have enough time to go into evals in this course because we were focusing like on a very specific way of doing RAG. But just know that if you look at a course or read a book about evaluation for AI agents, so that's one. The other one is evaluation for information retrieval or search systems. Principles from both of these are applicable here. All right, and then the easiest way to do eval is also like try to use LLM as a judge, etc. You can also like run automated eval jobs as well. And you don't have to use like VBA RAG eval or something. Like any sort of LLM application that you're building right now, like tools like Langsmith or LangFuse, they come baked in with regression testing suites. So this is just basically for those of you who are not aware, you have some data set, you have like test cases, right? Like that's what it is. You have test cases, unit tests, and then you sort of collect them in a database. And then whenever there's a major change to your system, you can run all of your system on those test cases again and see if there's a regression, if like some tests start failing, etc. Right? And this can help you guard against any sort of drift that can happen when you make changes to your system that doesn't account for making sure that the old things that work stay working, right? And then one thing that you can do is use state persistence. So LangGraph works with like state snapshots. So if you are persisting state, if you have workflow, if you have 3 steps, you can persist the state at every step, like to a local disk or local DB, whatever. If let's say you want to run your workflow again, and your query had already run up till the, let's say, document evaluation step, you can, a good thing about LangGraph is that you can execute that graph from step 3 directly. You don't need to do step 1 and 2 again, since you have the outputs of those already. So use those when needed, right? And try to like isolate orchestrator, retrieval, and inference. What I mean here is that RAG system, agentic RAG systems can get quite complicated, as we saw here. So you would need to like isolate if the problem is like low retrieval quality, which can happen here, or is the problem like low router quality, or is the problem at the step. So always try to isolate different parts of your system. And that's where tools like Langsmith and LangFuse come really handy, because they allow you to check the like step-by-step outputs, right? So don't look at the entirety of the input-output to debug. Look at the isolated problems that happen. Okay, so we have around 30 minutes left, and I really want to cover the last notebook, the last exercise that we have, because we built a really cool system here, and I want to walk you all through that. So let me share my screen one more time, and let's cover our complicated agentic adaptive RAG pipeline. Okay, I think my screen is visible now. So let's do this. So we what we basically want to solve in building this pipeline is that we had the problems of multi-hop queries not being answered, right? And we had the problem of like complex queries, or like queries where we retrieve documents that are not relevant being not relevant from the vector DB, and then adding to the noise. So there are multiple problems that we want to answer. So this is like one pipeline that where we try to solve all of these problems at once. So basically what we'll do here is that we'll build a pipeline where we analyze the query complexity to figure out the best retrieval strategy. We have the capability to search multiple collections. We had this in our router. We have some evaluation of results through corrective RAG mechanisms. We have some sort of query rewriting, as we'll see, is necessary, especially for sequential decomposed queries. And then we have like some sort of self-correction to make sure that we can use feedback loops. Okay, so before I walk through the code, let me take a different approach. Let me just say that, let me show you all what we're going to build. So we're going to build this graph. So, and we're going to use a feature of LangGraph known as subgraphs, where we can define a graph, like we can define a complete graph within a node. Okay, so what we'll build is a workflow which on the highest level has these 3 steps. We get a query, we do some analysis on the query. Based on the analysis of the queries, we may have a single query, or we might have like multiple different queries. We will, nevertheless, whatever we have, we will process them all in this process queries node, and then we will generate our result. So this is what our graph looks like at a high level, okay? Now, when you want to process queries, for each query, we will run this subgraph. So this is the graph that I showed you all earlier. And again, there's a lot of code here, and it can get quite complicated. So I really urge you to use your coding agent to understand this after the course is done. But what basically happens in the process queries node is that for each query, we do this. So if we take the query, we first figure out if the query should be rewritten or not, right? So this is the first entry point. And if it's the first iteration of our loop, this really won't do anything for the query, right? Because obviously the original query doesn't need to be rewritten. So we route the original query to our 4 sources that we have, nothing different here. And a new node we have is the evaluate retrieve documents node, right? So this will basically evaluate different documents that we retrieve. And then if, let's say, we retrieve enough documents to answer the query, we will generate an answer for the query. And you can see that this node is called generate subquery answer, right? Because we're running this graph for all the subqueries. Okay, so if we don't retrieve any documents, then this is the corrective loop. We will loop back to the query rerouter, and then we'll try to rewrite the query and then do the same thing again in the hopes of generating the correct subquery answer in the next time around, right? So depending on if we can execute this query in sequence or in parallel, we will either run all the subquery. So like depending on whether the original query can be answered parallelly, or does it need a sequential execution for subqueries, we'll have like different mechanisms of how we execute this graph. So if it's a sequential execution, then let's say we have 3 subqueries, like subquery 1, subquery 2, subquery 3. then we will basically run this query. We will basically run subquery 1 first, like this graph, this whole graph will run for this. We'll get a subquery answer. Then we'll run this graph for this whole graph for subquery 2. And the cool thing about this graph is that the query rerouter node, it obviously works well for changing our query based on this retrieved documents, but the query rewriter node works really well for this use case. Like we saw this example of resolving, changing the subquery 2 based on results of subquery 1. Then the query rewriter node will be able to do that for us. And I'll show you an example of that. So with all that being said, the main idea is this, right? We have one major graph like this. We get the main query, the one complex query or not complex, whatever. We run some query analysis. Then we process our queries. And based on if we can process them in sequence, we can process them in parallel, or it needs sequential execution. We'll run all our subqueries through this one, and then we'll generate the final answer. Okay, this is how it'll work. So again, instead of walking through all of the code, let's just look at the design of the different components of the different nodes. Okay, so all of this is the same as the router example. So we have different collections, and we initialize like different LLMs for our different tasks. And again, we're using GPT 5.1 for everything, so it doesn't really matter. But we still have like 3 different objects because for some of these, we'll require them to generate some sort of different structured output. So just for simplicity, it's better to just have like different objects for the same thing, so that we can attach the structured output that we need for like the different ones, right? So again, we're focusing on the design, not the code. So design includes the state definition. So in our subgraph that we saw, the really complicated graph, we're tracking these things. So we're tracking the original query, we're tracking the rewritten query, any reason for rewriting, if it needs a rewriting or not. This is the Boolean. So this helps in handy when we need to, in the initial pass, we need to figure out if we should rewrite or not. Number of retries, of course. So this will help with our termination condition. And then the things for like routing, the docs that got retrieved. This is a new thing that we have, which is relevant docs. So let's say that this is a list of 5 docs that were retrieved. So this will have like only, let's say, 2 relevant docs, right? But we keep track of both, because if we are using a monitoring and observability platform, then we need to, know like all the state snapshot, and it includes the retrieved doc and relevant docs, because there might be some example where our filtering of our corrective RAG is not working correctly, and we need to make sure that we have the data to debug it, right? So this will help. And then we have the subquery answer. Ignore this parallel logger here. Again, feel free to look into it in your own time, but this is necessary to create clean logs when we run subqueries in parallel, so that it doesn't become very convoluted. Okay, so query router is exactly the same, not interesting. Document grading system. So this is the schema. So we're basically getting a yes or no if the document is relevant to the query or not, and then some reasoning. This is optional. You can choose to include or not include it based on whether it improves the accuracy in your use case. We have some prompt, again, like not interesting. You can look at it in your own time. And then we have a chain that we create, which basically like passes the document to the grading prompt. And then we call the evaluation LLM with it, right? And then we get the results back. So once we have done this, we basically have this evaluate documents function here. And I'm using async.io here to run the evaluation for all documents in parallel. And this sort of syntax, again, like don't worry about this. What we're basically doing here is making sure that for all the retrieved documents, if they were like 5 documents, we could run our grading chain in parallel on these using async.io, right? And then once we get the results back, we just like zip them up. And that's it. That's what the evaluation documents node will do. It will evaluate all documents in parallel. And then we have query rewriting and expansion, which is basically given some this is the schema for the structured output. So this includes a rewritten version of a query, and then like some sort of reasoning again. And then we have the generation prompt for the subquery answer. And this is exactly the same as the generation prompt for the final answer from this notebook and this notebook. So no changes here, right? And then we start defining our subgraph nodes and conventional logic. Again, I don't think this is super interesting, and it's very complicated to cover as well in the interest of time. But what you just need to know is that when you build your subgraph using conditional edges and all these sorts of things that we covered in parts, you'll end up with a graph like this. Okay, so this becomes your subgraph. Now, what's interesting is, again, the design, and the design includes the query analysis and decomposition part. We haven't covered this here, right? So basically, the first step in our adaptive RAG is just to analyze the query and figure out the processing strategy, right? And what we'll do here is that when we analyze the query, we will do these things. So we'll need to find out whether the query needs decomposition at all. So should the query be broken down into, whoops, let's close that actually. Yeah, so we need to figure out whether the subquery will be broken down into subqueries, whether a main query should be broken down into subqueries. So this is the Boolean, this can be true or false. And then we have a list of subqueries, which is, okay, if there's some decomposition, then these are the subqueries that are generated. There is then the execution plan that for the subqueries, a sequential or parallel execution is enough, right? The default can be, okay, like a parallel execution. And then some reasoning. So, and then I have some examples here in the prompt. So again, let's just ignore that and see the outputs of some test results. So for this query, what are the specs of the Ultrabook Pro 14? These are the outputs we get. It says that we don't need a decomposition, and like there's a reasoning, right? Like it's a singular, focused, and cohesive query, blah, blah, blah. And it doesn't need decomposition. So okay, all good. Not interesting. A query like this, what gaming laptops do you have, and what are the return policies? Okay, it needs decomposition because it's two queries in one, right? But they're not really relevant to each other. So the execution plan can be parallel. Okay, amazing. Similar for this one, right? Like battery life for ZenBook Air versus Ultrabook Pro. This is one of the problematic queries from exercise one. And again, like no decomposition needed. These are the subqueries. Decomposition needed, true. These are the subqueries, right? And like we can see, it has very clearly written the subqueries, awesome. And then it can be executed in parallel, amazing, right? And all good. So I don't think I have a example of sequential. Oh, I have actually later on. So okay, so we have tested out with some subqueries and it worked quite well. And then we have the design for our main graph. This is way simpler than our subgraph. All good. And then we have like a helper function to process a single query using the subgraph. And this basically initializes a state for the subquery, and then simply like invokes the query for that subgraph. And by the way, we'll use this helper function to run queries in parallel. That's why we have defined it like this. So yeah, the main graph, it has 3 nodes. Query analysis, it will do its query analysis using the query analysis chain. Okay, nothing complicated here. The process subqueries node, this is the interesting one. So what it'll do is that once the query analysis is done, it will get the subqueries from the analysis step. It'll get the execution plan and this. And then if we need to decompose, if we don't need to decompose, sorry, we'll just get the result of the single subquery, right? Like we'll just get the subquery as at index 0, which will be the only one there in the list. We'll get the result, and then and that's it, right? Like that's all there is to it. And after this block runs, we'll simply move on to the generation step. That's all the node will do for node decomposition. For parallel decomposition, we do the async IO pattern again. We run the subgraph for a single query in parallel for all the subqueries. So yeah, don't worry about this. This is just how you run things in parallel using async IO, using a list of tasks. Okay, and then you just process all the results by adding it to a list of all the documents that are being retrieved for the query. All right. And then the final case is that if sequential execution is needed, then we need to accumulate context basically. And what this basically means is that we start with subquery 1. So here we're basically starting with the first subquery. And the first subquery, we just say that if it's the first subquery, that it won't need a rewrite, which is going to be true here. Sorry, it'll be false here. And then we just run this subgraph with this, right? So once we run the subgraph for the first subquery in the sequential step, we get the results back, we extend the documents, and then we sort of start accumulating the context, which is basically results from the first subgraph, like what all is in there from that answer, right? And why we want to do this is because we want to use that for our subquery. So what will happen now in the second iteration of this loop is that the second iteration will have the second subquery, and it will have the results from the first subquery here. This is what we're accumulating outside the loop, right? Now, this will be true because 2 is greater than 1, right? So needs rewrite. Now what will happen is that we process the single query again, like the subgraph. We pass in the query. We pass in that, yes, rewrite is needed. And we pass in that, okay, this was the context from the previous subqueries, right? And all the subsequent subqueries will have this accumulated context here. And we'll see how this is used in a moment. So all this is done. We generate a final answer from this. Okay, not, super great. And this was the graph. So let's see the results from some example queries. So I think parallel decomposition, not super interesting here for me. But let's just go and check the example of the sequential decomposition one, because I think that one is quite good. So yeah, so let's say you ask a query, find me the best mouse and check if it has any issues. Now, of course, you have to find the best mouse first. And then you have to check if it has any articles in the troubleshooting database, perhaps, right? To check if there are any frequent issues or something. So that's what our pipeline will do exactly. And this is all log, this is all real output. So you first have this main query. You say that, okay, it needs decomposition. And you say that your initial subqueries are find me the best mouse and check if the best mouse has any issues. Notice I say initial subquery, right? Because we'll rewrite this query before we run it. So, okay, let's start. It starts executing the 2 queries sequentially. So for the first subquery, it skips the rewrite, obviously, because no need. And it does the routing. It gets some documents back. You can see that it's doing some evaluation. It finds some relevant documents. Awesome. It finds some, it deems that all documents here are relevant. And it doesn't need to do any rewriting for the first subquery. And it gets an answer back, right? It says that the best mouse that TechMart has is this GlideX Pro, and it has these features and blah, blah, blah. Now the first subquery is done processing. Now what happens in the second sequential step is that it gets this query. This is the initial subquery we have. This is the second initial subquery. And then we need to rewrite it, right? Because this needs to be more targeted. We need to check if GlideX Pro has any issues. We don't want to check if the best mouse has any issues, right? So given this previous context, which was the answer from the first one, this is the accumulated context till now. It says that, okay, this is the original query, and it rewrites it to, okay, check if GlideX Pro mouse has any known issues, problems, etc. So this is amazing, right? Our system is working as expected. It's able to rewrite the second subquery based on results of the first one, which is what we wanted, right? And you can see that it even says in its reasoning that it has incorporated a specific product name and previous context, etc. Right? So awesome. Now it sort of continues to the same loop. It finds any relevant documents. It says that, okay, all documents that retrieved are relevant. And then it generates the answer of the subquery. And this will be the final answer, right? That, okay, it found that the best mouse is this. And then these are the issues that it might have, right? It's a highly rated option, but it might have these issues. So it worked quite well. While in a parallel decomposition query, what will happen is that we have this large query, what laptops do we have and what other return policies. Actually, let me check the other example where we wanted to compare the battery life of two products. I don't know if I have it here. Yeah. So like battery life of ZenitBook versus Ultrabook. So it says that, okay, decomposition needed. These are the two subqueries, execution in parallel, okay? And then it just executes those subqueries in parallel. So this is the first one. You can see that it gets some documents. You can see the collective RAG in action here. It got some document about ZenitBook 12 Evo, and it says that, oh, it's from a different product. So this is an irrelevant doc. And then for this one, it says that, okay, it only found two relevant docs, right? No retry needed, but it will only pass in the two relevant docs to produce the final output. Amazing. And then for the second subquery, it does the something similar. And then you can see a final answer, right? Where we successfully have decomposed the complex query. We have ran two subqueries in parallel for two different products. And then we created a good comparison and summary of the battery life of these ones. So, and this was the sort of query that we were not able to solve in basic RAG. So I know this is a lot to cover and there's a lot of code in this notebook, but it's quite fun. I think it's quite an interesting problem. It's quite an interesting workflow. So please, after this course, we only have like 5 minutes left now. Please, in your own time, just run your coding agent on this notebook. Try to figure out what's happening. Try to make some tweaks to the workflow and see if there are some queries that work really well or really fail with this one, or what improvements you can make here. I think this is the sort of learning that's more important, that will be helpful in making sure that you internalize the concepts of how agentic RAG graphs should be designed, right? Okay, so this was all for the coding section, and we're about at the end of time here, right? So what are the key takeaways? So I think the first one is that RAG remains essential for grounding LLMs in real world and up-to-date information. There's no getting around to not having RAG right now. And agentic workflows can bring adaptability, autonomy, and iteration to traditional RAG pipelines, like we saw in plenty of the examples that we covered. And LangGraph is just one of the frameworks. There are others that can be used to build agentic RAG systems. And agentic RAG patterns like query analysis, routing, all of these can be composed modularly, like Lego bricks, right? And always try to balance performance and cost by using strategy-aware design, smaller models, and some sort of caching. And like, as I mentioned, please, start with the notebooks, clone this repo, run your coding agent on it, and just try to adapt these workflows and see what sort of systems you can build. And then try to think of ways to take the parts here, take the design patterns that you learned here, and include that in your own projects, right? You can start with templates for these notebooks, and then you can use them to compose your own agentic workflows. And try to incorporate some sort of eval-driven development and logging tools to refine your pipeline. The main idea that I covered is that once you've started using some sort of observability framework like LangSmith or LangFuse, you will have more visibility into what parts work really well in your workflows, what nodes work really well, or what nodes are failure nodes. So then you should be able to start iteratively refining your workflows. Okay. And then, of course, you can read this fantastic book that's available on the O'Reilly platform that can cover more concepts from AI engineering as well. So I think I have a couple of minutes to answer some questions. So let me see if we have a good one that I should really cover. So let's see. Yeah, so this one we covered, right? Is it good to have the entire org data in one vector store, or segregate into multiple stores and do query routing? I covered query routing, since you can have different collections and route to different collections based on the parameters of the query. and route to the right collection, avoid all these source selection problems. That's one way. What I didn't cover is how you can use metadata filtering to do something similar. So let's say you have all your documents in one vector store. Okay, what you can do is you can have some sort of metadata attribute there. Let's say for category of the query or like type of document, like FAQ troubleshooting, you can have that in metadata. So what can happen now is that through like your query analysis step, you still need some query analysis step, right? Like, which is what query routing is. What you can do is you can extract a parameter that, okay, this is a troubleshooting type of query. And then what you can do is instead of routing, you can implement the metadata filtering to only get documents for that category when you're doing your vector search. The philosophy is the same, but there are like multiple ways to do it. It's always better to have some sort of structure where you can categorize and group these documents correctly, right? So that you can use your results of your query analysis. All right, so let's see if we can move on. Yeah, just one question. There's one question that says, how does OpenRouter apply here? So OpenRouter is basically a LLM gateway. You can use OpenRouter to use any LLM in your applications without necessarily having to write different like sets of code for different LLMs that you use. It provides you a centralized interface for different LLMs. So OpenRouter is different than query routing. Please don't be confused by both. One is an LLM gateway, one is a concept to cover building agentic RAG pipelines. All right, and then with that, we have come to the end of the course. There are, I'm sorry about not being able to cover all of the questions. There's quite a few good ones that I see that I haven't answered. If you reach out to me on LinkedIn or by email, which links to which are in the slides, I will do my best to answer some of the burning questions there. But yeah, like it was great teaching this course again, and I would like to just hand it back to Derek now. So all yours, Derek.
All right, thank you so much, Sajal, and thanks everyone for attending. In just a moment, you'll see a course evaluation on your screen. If you could take a quick minute to fill that out, it really means a lot to us, and your feedback is always much appreciated. Additionally, I did see some questions about the recording for this course, and I do just want to remind everyone that you will receive the recording link in your email, and you should get that within 24 to 48 hours from now. So with that, we'll go ahead and wrap up the session. Take care, enjoy the rest of your day or night, and we'll see you next time.